Hi everyone, welcome to PrepFusion. So in the last lecture we were studying about diffusion current density, right? And in the diffusion current density, in the last I told you that we will be studying about Fermi direct distribution, that we will be commenting on the probability of finding an electron. But I changed my mind, I changed the slide, and now first we will be studying about your semiconductor under non-equilibrium. Okay, so we will be keeping our semiconductor under non-equilibrium. What was our equilibrium condition? That our equilibrium condition, mass action law was valid, right? Number of electrons multiplied with number of holes, that value will be constant. If it was intrinsic, number of electrons were equals to number of holes. So n into p is equals to ni square. If it became n type, the number of holes, the number of electrons got increased in n type, but the number of holes got decreased. So multiplication was constant. So this was our equilibrium condition. Now the equilibrium will be disturbed. Something we will do. What we will do is that we will throw light on the semiconductor. Because we are throwing the light, light is having some energy, and because of that energy some electron hole pair will be generated. So they will disturb the equilibrium condition. So that phenomena we need to study, but that phenomena will come, but that will take some time. For the first 30 minutes we will be discussing some discrete topics, like this question is there, then another question would come, then we will make some conclusion. So for the first 30 minutes you will feel like that, sir, we are understanding everything, but the topic is combined, not making any sense. That you are teaching one topic, two topic, three topic, but combined it is not making sense. It will make sense in the end of the video. So you need to have some patience here. Okay, so just keep on watching on the screen. If I tell you something to remember, then only you need to remember. Otherwise just keep on watching, keep on working in your rough notebook, and have the patience. Everything will make sense in the end. All good for you? Okay, and this topic is considered as a typical topic. Okay, usually students find it very difficult in the whole EDC, in the whole subject I am talking about, not only in basic semiconductor physics. In the whole EDC people find it difficult, but we will understand in a very good manner. First we will build up some base, and then we will move to the topic. Okay, so let's get started. You need to solve this question. Since you have already studied about drift current and diffusion current, you would be able to solve it. What is given? Electric field is 0. The total electric field is 0, and these are the carrier profile. This is the, let's call it number of electron, let's call it p type, let's call it n type semiconductor. Okay, this is the n type semiconductor, and this is the profile of electrons, and this is also the profile of electron with respect to distance x. You need to find the value of dj by dx. And what is j? J is total current density. J is total current density. That means in this total current, drift current will also come, and diffusion current will also come. Drift and diffusion, both of the component would come. Okay, so for the first one, you let me know. Let's just say in both of the cases drift current would be 0 only. Why is that so? Because what is the formula of drift current? So the formula of drift current is, let's call it case A and let's call it case B. The formula of drift current is NQ NX, since it is varying. So NQ mu n E. And sir, since this is 0, in both of the cases drift current is 0. I don't need to think about drift current. Only thing I need to think about is diffusion current. So in the first case, let's talk about the diffusion current. What is the diffusion current? In the first case, there is no concentration gradient. That means concentration is same. It is uniformly doped. Since it is uniformly doped, that means there is no concept of diffusion current. Because what is the formula of diffusion current? Q dn dnx by dx. What is the slope here? 0. So what will be the answer? 0. So for the first case, drift is 0, diffusion is 0. So total current is 0. So for the first case, total current is 0. And if you differentiate, what will be the differentiation of 0? That would be 0 only. Okay. Now for the second case, drift current is 0. What about the diffusion current? So here you can see that the slope is constant, right? What I mean to say is that dnx by dx is constant. So what will be the value? Q dn into some constant. This is constant, this is constant, this is constant. So whole value is constant. Whole value is some constant, and this is equals to the total current, because drift current is already 0. So what will happen? If I differentiate this total current, what I will get? Constant plus 0 will be constant. What will be the differentiation of constant? That would be 0. So under 0 electric field, if your profile is either constant, if your carrier concentration profile is either constant or linear, then the differentiation of current density with respect to x will be 0. Sir, why we are focusing on this quantity? We will understand that. Have some patience. But you understood that if there is no applied electric field and the profile, the concentration profile is either linear or constant, then the differentiation of current density with respect to x, that would be 0. All good? All fine? Solve the similar thing for this question. The profile is constant. What does that mean? Diffusion current is 0. Right? Diffusion current is 0. And what about the drift current? Drift current will be n q mu n into E. E is constant. E is some constant. E is some constant value. So the whole value will be constant. Right? If the whole value is constant, that means this complete Jx is constant. And if this complete Jx is constant, then the differentiation is also 0. So only in 3 conditions you are getting differentiation equals to 0. There are only 3 conditions where you are getting this differentiation equals to 0. What is the first condition? That electric field is 0, profile is constant. You don't need to mug it up. You will be able to think, okay, electric field is 0, profile is constant, drift, diffusion, both 0, differentiation will be 0. Second case, electric field is 0, drift is gone. Nx is linearly varying, okay, concentration is linearly varying, that means dnx by dx would be constant. So if you again differentiate it, then that would be 0 only. So here also dgx by dx will be 0. And third case, diffusion is gone, drift is constant, and differentiation of a constant value will be 0 only. So these 3 cases, you don't need to mug up these cases. But if these cases are coming in front of you, will you be able to tell the answer of this particular thing? Yes. But now why we are focusing on this djx by dx? What it is representing? What is J? J is current density, right? I by A. And here there is dx and this is di as well. So what will be A into dx? Volume, right? So let's understand that. What we mean to say is that, let's just say this was a semiconductor. Semiconductor will be a 3D, right? It will be a 3D material. Let's just say this is a semiconductor. In this semiconductor, I am taking a very small area. Although this looks like a very big volume, but I am taking a very small volume. In this semiconductor, I am taking a very small volume which is having a length of dx and cross section area of A. Cross section area of A. Length of dx, very small length I have taken, but cross section area will be A only, right? Cross section area of A. So what your A dot dx will represent? It will represent the small volume, right? Now what I am saying, what does 1 by q dgx by dx represent? First let's talk about dgx by dx. What does this represent? What is J? I by E. Sir, you are saying that current is a function of x. Yes, it could be a function of x, right? N q mu E, right? Current could be a function of x. Here you have already seen. This is very simple thing. Yeah, so current would be a function of x. So what I am saying is that this is I by A dot dx. So this I can call it as per unit volume. So this is nothing but current per unit volume. Say yes or no? dgx by dx shows current per unit volume. All fine, right? Now what is current? Current is q by t. Sorry, not q by t. I should say total charge divided by time. Current is total charge divided by time and dot dv. So what this quantity is representing? Total charge per unit volume per unit time. dgx by dx is representing a total charge per unit volume per unit time. Now what is total charge? Let's just say in this particular semiconductor I am having only 1 electron. So what will be my charge? Q. If I am having 2 electrons, charge will be 2q. If I am having 2 electrons and 2 holes, that means carrier concentration is 4. 2 electrons and 2 holes, that means total charge will be 4q. So if I am saying that my carrier concentration is N, capital N, if my carrier concentration is capital M, then what will be the total charge? N into q. Total charge will be N into q. And now if I divide this quantity by 1 by q, if I divide this quantity by 1 by q, if I divide this quantity by 1 by q, so what will happen? Q and q will get cancelled out. So what is 1 by q dgx by dx is representing? It is representing the number of charge carrier per unit volume per unit time. So 1 by q dgx by dx represent number of charge carriers in per unit small volume per unit time. Is that clear to you or not? How we started? dgx by dx, what is your current density? I by A. If I see here, A dot dx becomes the volume, right? Area multiplied by the length. What it would become? It would become the volume. So it is like current per unit volume. Now what is current? Current is charge by time, total charge by time. So total charge would be the number of charge carrier into Q, right? Number of charge carrier into Q, because one charge carrier would be having a charge of Q, right? So total charge will be NQ. So now if I cancel out Q with Q, then what this 1 by Q dgs by dx is representing? That is representing number of charge carriers per unit volume per unit time. So number of charge carriers either can come into this, or it can come, or it can get out of this. Basically, either the number of charge carriers can increase here, or it can decrease. Are you able to understand this point? Let's just say some current is coming, some current density Jx is coming. Okay. So what will be the current density going out? I am calling this as Jx plus dx. So if the going out current is more, what does that mean? That means dgx by dx is positive. I hope you know this thing, right? If basically if you draw a graph of y versus x, simple mathematics, on this point your slope will be positive, on this point dy by dx is positive, and on this point dy by dx will be negative. What is the reason behind that? Because here y is increasing, right? So if I say if my current density is increasing, that means this current, this going out current is more. So if dgx by dx is positive, that means going out current is more. And if dgx by dx is negative, that means going out current is less. Basically input current is more and going out current is less. If this is the scenario, then dgx by dx would be negative, right? And if output current is more and input current is less, then dgx by dx would be positive, right? All these will make sense, just have some patience. Some more points we will see. Okay, all these will make sense for continuity equation. Usually continuity equation is studied with respect to a lot of mathematics, but we will just reduce it in a very short manner. So till this point what we have understood. So this 1 by q dgx by dx represents the net outflow or inflow of the number of charge carriers per unit volume per unit time due to the current. Is that clear to you? So whatever the thing that I wrote down here, that you can write down in a rough manner. In rough manner in your notes you can write down what 1 by q dgx by dx is representing. The total inflow or outflow, because either the charge can get into it or the charge can get out of it. So inflow or outflow of total number of charge carriers per unit volume per unit time due to the current. Is that clear to you? And if dgx by dx is positive, what does that mean? That means current leaving the small volume is more than the current entering into it. And if dgx by dx is negative, that means current leaving the small volume is less than the current entering into it. All good? That means current entering is more, leaving is less. That means dgx by dx would be negative. And if current going out is more and entering is lesser, then dgx by dx would be positive. All good? Now this is a very, very important point. People just mug it up. Every student will just remember it, but we will understand what I am saying. Number of electrons increased per unit volume per unit time, what that quantity would be equals to. So let's just see it. This is our small volume, right? Now I am saying that the current entering and this is the current flowing out. I am saying that current flowing out is more and this is less. Okay, current flowing out is more and current flowing in is less, right? The electron will always move opposite to the direction of current flow, right? Electron always moves opposite to the direction of current flow. Let's just say the current is flowing in this direction, then electron would surely be moving in this direction. So if the current is flowing in this direction, so where the electron would be moving? Electrons will be moving in this direction. Now you are saying that current flowing out is more. That means electrons getting in will be more. You are saying that this current is more and this current is less. That means the current flowing out is more. That means electrons getting into the small volume will be more and getting out of this small volume will be lesser. Say yes or no. You are already saying that dgx by dx is positive. If dgx by dx is positive, what does that mean? That current flowing out is more. If the current flowing out is more, that means current that means electron entering into the volume will be more and electrons entering out will be lesser. So what do you understand? If dgx by dx is positive, that means the value of current, the value of electrons inside the volume will increase. Are you able to understand this point or not? A very, very typical point. No one is going to explain you with this intuition. Believe me, they will needlessly use any mathematics and you will just write down, okay, you will be happy. But use your intuition, use your brain here. Current entering out is more. That means the electrons getting into will be more. What I need to write? I need to write the number of electrons increased per unit volume. That means here what will be my answer? 1 by q dgx by dx. Because what is 1 by q dgx by dx represent? 1 by q dgx by dgx by dx represent the net outflow or inflow of a number of charge carriers per unit volume per unit time. So here what is happening? The charge carrier is getting increased and we are considering the charge carrier to be electron. The charge carrier could be electron, it could be hole as well. But for the electron what is happening? If your output current is more, that means if you are considering that dgx by dx is positive, then what is happening? The electrons are actually getting increased inside the volume. All good for you? All fine? Do the same for hole and let me know what will be the answer. Here I will write down djn. Why jn? Because it is about the electrons. Do the same for the holes and let me know what will be the answer. If I say this current is more and this current is less, that means djx by dx for holes I am saying that it is positive. I am saying that it is positive. This value is positive. So current getting out is more. Holes will always flow in the direction of current, right? If this is the direction of current, so this will be the flow of holes. So lesser current is going in. That means lesser holes are going in and more current is getting out. That means more holes are getting out. So what will happen? The density of electrons inside this small volume will decrease. Not electrons, sorry. The density of holes inside this small volume will decrease because more holes are getting out. Is that clear to you? If dgx by dx is positive, that means this current is more and this current is less. That means more holes are getting out and less holes are getting in. That means density of holes inside this small volume is getting decreased. But what you need to write down? You need to write down number of holes increased. If you need to write down number of holes increased, what does that mean? That means you will have to put a negative sign here. Is that clear to you or not? That means the current entering would be more and the current getting out would be less. If current entering is more, that means number of holes entering are more. And if current getting out is, number of holes entering would be more. And if current getting out is less, that means number of holes getting out is less. So here the hole concentration will increase. That means you need to take dgx by dx as negative. So this value is negative, negative would eventually become positive. So this is showing the number of holes increased. If you cannot understand it, which is I have given good enough explanation, I hope you will be understand. If you are not able to understand, then just by remember a trick. When you wrote down the diffusion current, so for electrons, how did you write it down? Sir, nq dnx by dx. Sorry, dnq dnx by dx. And for holes, what you did? Sir, dpq dpx by dx and another negative sign. So for holes you are using the negative sign, for electrons you are using the positive sign. So in the whole EDC you will do the same thing, that for electrons you will use the positive sign and for holes you will use the negative sign. But the content that I explained here, that you are not going to find in the textbook. Okay, it is very, very intuitive, and within one line we will be writing down the continuity equation. Otherwise you see in the notes the derivation of continuity equation will take 2 pages, but we will write down only in one line. In one line only you will see the continuity equation. Do you remember the pointing theorem? Pointing theorem you might have studied in your semester examination. That also takes 2-3 pages, but in one line we write down the pointing theorem, only in one line. Similar thing we are going to do with the continuity equation as well. In one line we will write down the continuity equation if these particular basics are clear. I hope these basics are clear to you. So what we started with, first we started with when dgx by dx is 0. So that condition we have seen when it is 0. So if you can remember, you can remember. Otherwise, this condition will be mentioned in the examination. Okay, this condition will be mentioned that E is equals to 0. This is the profile. If this condition is mentioned, then you will be able to derive that both are 0. Okay, or this condition might also be mentioned. Then also you will be able to derive that this would be equals to 0. Now, why we are focusing so much on dgx by dx? Because dgx by dx represent a particular quantity. So 1 by q dgx by dx is representing the number of electrons or the number of charge carriers flowing in or flowing out per unit volume per unit time. Okay, and if dgx by dx is positive or if it is negative, then you would know the meaning. And number of electrons increased per unit volume per unit time is given by 1 by q djn by dx, and number of holes increased per unit volume per unit time is given by minus 1 by q djp by dx. Within 30 seconds you will be able to revise these slides. Now this is a very simple thing. If a light is having a wavelength of lambda, then what will be its energy? So energy of light is given by E equals to h mu. Okay, and mu is equals to c by lambda. These formula we have studied in our elementary classes. Not in elementary classes, in class 11 12th we have studied these formula. The energy of a photon, light means photon only. Okay, light means photon. So the energy of a photon is given by E equals to hc by lambda. Okay, now this has a typical value, hc has a typical value. What is h? H is Planck constant. What is the value? 6.63. H is Planck constant having a value of 6.63 10 to the power minus 34 joule into second, right? That would be the value. And C you already know, 3 into 10 to the power 8 meter per second. So when you solve all these things, then you get a particular answer which you should remember. 1242 electron volt nanometer divided by lambda. Divided by lambda. So value of hc is, if you multiply h with c, then what answer you will be getting? You will be getting the answer in joule. Joule into meter. The answer you will be getting in joule into meter. And then you convert it into electron volt. So the way you convert it into the electron volt, and then final answer will be this. 1242 electron volt nanometer. Okay. Now let's just say lambda is given as 10, not 10. Let's just say lambda is given as 36 angstrom. What is the value of angstrom? Angstrom is 10 to the power minus 10 meter. If you don't know, just write down 1 angstrom. This is known as angstrom. That is equals to 10 to the power minus 10 meter. So can you convert it into the nanometer? Yes, that would be 10 to the power 1 minus 1 nanometer. So here what I will write down, 10 to the power minus 1 nanometer. So nanometer to nanometer will get cancelled out, and what will be my final answer? My final answer will be 1242 into 0 electron volt. 12,420 electron volt. So your energy of the photon will be 12,420 electron volt. Try remembering these data as well. Okay, both of the data you should remember. 1242 electron volt nanometer, because a lot of time they will be asking the energy in electron volt only. So there you will not be converting. You will just remember 1242 electron volt nanometer divided by lambda. All good? All fine? So everything will make sense. Just have some patience. Now there are two things, generation and recombination. These things I have already discussed. Let's just say I was having a semiconductor, right, at 0 Kelvin. So at 0 Kelvin, in the valence band I am having all the electrons, and in the conduction band I am not having any electrons. So what really happened? Just as I increase the temperature, what will happen? Some covalent bond will be broken from here, and some electrons from the conduction band, some electrons from the valence band will go into the conduction band. So this electron from the valence band is going into the conduction band. This electron from the valence band is going into the conduction band because of the temperature. So this process is known as generation. Generation of electron hole pair. Generation of electron hole pair, right? So in a semiconductor, when energy, it could be heat, it could be light, when the energy is given, new electron hole pairs are generated. This process is known as generation. And what is recombination? So this generation process will keep on going, but you know that there will be some equilibrium condition, no? If it is intrinsic type of semiconductor, or if it is not intrinsic, then this condition would be there, no? N naught equals to P naught, N naught into P naught equals to Ni square. So what may happen is that some electrons may fall back as well. like what will happen, these electrons will spend some time, these electrons will be spending some time in the conduction band and they may fall back as well. So let's just say this fall back, then what will happen, this might generate electron and a hole pair. So basically if this electron is falling back into the hole, that means from electron from the conduction band is falling into the valence band, then whatever the electron hole pair was generated, that is destroyed. Because initially what was the scene, this was the electron, but what happened was this electron went here and hole was created. Now what really happened, the electron has fall back. So if the electron has fall back, so this vacancy is gone and here there is no electron. So now eventually the same condition we have got. So this process is known as recombination, like the electron hole pair being destroyed. Here electron hole pair are being generated and here electron hole pair are being destroyed. So what is written? An electron and a hole can meet and cancel out each other. When this happens, they both disappear. Electron fills the hole and energy is radiated. Okay. So when the electron is going from here to here, when the electron is going from valence band to conduction band, then it was taking some energy. It was taking some energy because of the temperature, right? Or it could be because of the light, or it could be because of any heat. So it was taking some energy. Now when the electron is falling back, it will release some energy. Okay. So whenever electron gains some energy, so here it is gaining some energy. Now if this electron is falling back into this hole, then it will release some energy. So here energy was given, now here the energy will be released. So whatever the energy was given, the same energy will be released, right? If it is falling from the same level, what I mean to say is that, let's just say this gap was 1.1 electron volt. Okay, so you have to give 1.1 electron volt energy, then it will reach here. Now if it is falling from here only, then it will release 1.1 electron volt only. Like whatever the band gap is there, it will release the energy equal to that only. But it might happen that it is falling from this level. So first what will happen, it will fall from here to here and then it will fall from here to here. So here also it will release some energy and here also it will release some energy. Okay. Although these are not important for the conceptual purpose, I am just telling. So whenever electron gains some energy and if it falls back, it will release some energy as heat or light. And we have already seen when it releases the heat and when it is releasing the light in the last lecture only, when we studied about direct and indirect band gap semiconductor. Okay. So if there is a momentum change, then it will generate the heat, otherwise light. Okay. So these are just two basic terms I wanted to tell. Now we will revise our RC circuit. Sir, suddenly why RC circuit? Everything will make sense. Have some patience. So this was your system. This was your RC circuit. If I apply 5 volt to it, on this RC circuit, if I am applying 5 volt, then what will happen? This capacitor will charge. This capacitor knows that I want to charge till 5 volt. This capacitor knows that I want to charge till 5 volt. But will it charge instantaneously? No. Right? What will happen is that it will take some time to charge. It will take some finite time. The capacitor knows that I need to charge till 5 volt, but it will not charge instantaneously. Any system doesn't respond instantaneously. You turn on the fan. You want to turn on the fan at a speed of 5, but will it, just as you click on the button, will it be moving at a speed of 5? No. First it will get a speed of 1, 2, 3, 4 and then it will come to 5. Right? So in the similar manner, this RC circuit, if you give 5 volt to it, the capacitor knows that I want to charge till 5 volt, but it will not instantaneously charge till 5 volt. It will take some time and then it will reach. Let's just say it was taking a time of t1 only. So till it took the time of t1 and it has reached till 5 volt, right? Now at 5 volt, what you have done is that you have changed the switch. Initially you were giving 5 volt supply. Now what you have done is that you have connected it to the ground. So what will happen? Whatever the initial voltage that it has developed a 5 volt. Now it knows that I need to deliver all the voltage to the ground. But that means I need to deliver all the energy to the resistor. That means this will be completely discharging. So capacitor will be discharging from 5 to 0 volt because you have removed the source and you have connected this to ground. So capacitor will discharge. It will discharge from 5 to 0 volt. Now capacitor knows that I need to go to 0 volt, but but will it go instantaneously? When you turn off the fan, The fan gets turned off instantaneously or it takes some time? It takes some time, right? From 5 to 4, 4 to 3, 3 to 1 and then to 0. So similarly, this will discharge, but it will take some finite time. And these time depend on some time constant that is known as tau, RC. Now there are two kind of steady state. You can either call this as steady state, because when you gave the 5 volt, this was the steady state, that at I have reached the 5 volt, and just as you removed the 5 volt, then this could be the steady state, because after removing the 5 volt, when you are getting the 0 volt, this could also be known as steady state. Steady state means your voltage is not changing with respect to time. Steady state means your voltage is not changing with respect to time. If you have turned on the fan, then let's just say now fan is moving at the speed of 5. So it will continue moving at the speed of 5 only, right? So now the speed is not changing. So that is known as steady state. With respect to time, nothing changes. So steady state, the word steady state is defined with respect to time, not with respect to distance. Okay. So what I will be writing down, the meaning of steady state is with respect to time, not distance, or I am just writing down x. And steady state and constant both are the same thing. Constant is defined with respect to t. That means your value is constant. It is not changing with respect to time. And if I say uniform means it is not changing with respect to x. When I was saying that this electron concentration is having uniform profile, we are having uniform doping. So what is the meaning of uniform? Uniform means it is not changing with respect to x. And if I say constant, that means I am talking about time. So this thing we use in EMFT as well. In EMFT as well, I say the same thing. There is a difference between uniform and constant. Constant means, just look at the last word, constant, t. T means time. So if I say something is constant, that means it is not changing with respect to time. And if I say something is uniform, that means it is not changing with respect to distance. Okay. So with respect to time, not distance. Here, instead of writing x, better let me write down distance. And constant and steady state both are the same thing. Okay. Constant is nothing but a steady state only. Well and good. Now slowly we are moving towards our topic. Why we studied so, sir? All these things I already know. I have studied my network analysis. I already know all these things. Sir, why we studied it? You will understand. Have some patience. Okay. Now our semiconductor under equilibrium we have seen. In intrinsic semiconductor, just 1 second guys. Yeah. Sorry for the interruption actually, like in between if I feel too much of cough, then I need to stop, right? I hope you guys are not getting irritated of it. Please don't get irritated and focus more on studying, not on these things. My health is never improving. The number of charge carriers with respect to distance x I am drawing. Okay. So I know that if uniform doping is there, so let's just say this is my semiconductor. So I know that number of electrons will be equal to number of holes, and that will be equal to number of intrinsic carrier concentration in intrinsic semiconductor at thermal equilibrium. That means temperature is constant. Now I am not increasing the temperature, I am not decreasing the temperature. If I am at 300 Kelvin, then yes, now the number of electrons and number of holes are 10 to the power 10 centimeter cube inverse. Roughly this value for silicon. So this value is constant now, right? And this is not changing with respect to x. Why so? Because this is uniform doping, right? So under uniform doping we are considering. So I know that number of charge carriers, that would be number of electrons will be equal to number of holes will be equal to Ni, right? This 0 I am putting, it is showing that under equilibrium. Okay. What about the n-type semiconductor? In n-type semiconductor, you would know that number of electrons would be more, and here you know that number of holes would be more, right? And here number of holes will be less, and here number of electrons will be less. So what I will write down here? What I will write down? Number of electrons in n-type semiconductor at thermal equilibrium. Number of holes in n-type semiconductor at thermal equilibrium. Number of holes in p-type semiconductor at thermal equilibrium. And number of electrons in p-type semiconductor at thermal equilibrium. Okay, so just the notation I am telling. number of electrons in n-type semiconductor at thermal equilibrium, number of holes in n-type semiconductor at thermal equilibrium, number of holes in p-type semiconductor at thermal equilibrium, and number of electrons in p-type semiconductor at thermal equilibrium. This value will be more than this because it is for p-type. Here electrons will be more and here both will be equal. All good, all fine. And in all of the scenarios, the mass action law will be valid, right? What will be the mass action law? Will say n naught into p naught will be equals to ni square n naught number of electrons in n-type semiconductor at thermal equilibrium, number of holes in n-type semiconductor at thermal equilibrium, and number of holes in p-type semiconductor at thermal equilibrium and number of electrons in p-type semiconductor at thermal equilibrium will be equals to ni square. So these mass action law will also be valid. But now what I am doing, my semiconductor was happy. Here it was lying very happily. But now what I will do is that I will expose it to some external source, and that external source I am telling as light. So what was the condition? I am assuming that my n-type semiconductor is under equilibrium. So it is having a certain number of holes, it is having a certain number of electrons. So number of electrons per unit volume in n-type semiconductor under equilibrium, number of electrons in n-type semiconductor under equilibrium. Let's just say I am giving 10 to the power 16, and I am saying that my intrinsic carrier concentration is 10 to the power 10. Okay, this is my intrinsic carrier concentration. When it was intrinsic, this much number of electrons and hole was there, right? So what will be the number of what will be the number of holes in n-type semiconductor at thermal equilibrium? That would be 10 to the power 4. If you are not able to understand this, that sir, from where this 10 to the power 4 came, that means you are not studying. Mass action law, right? 10 to the power 16 into 10 to the power 4 will be equal to 10 to the power 10 whole square. So this you should be able to understand. So this was the condition of thermal equilibrium. Everything was fine. But now what I am doing is that I am throwing a light. What I am doing? I am throwing a light which is having an energy of h mu. And this energy h mu is greater than this band gap. On this semiconductor, I am throwing a light having an energy of h mu which is greater than this band gap. Now what will happen? Already number of electrons were there, already some holes were there. But because of this light, these electrons will get enough energy that these electrons will be moving from the conduction band to valence band. Sorry, valence band to conduction band. I am saying opposite. The electrons will get enough energy to move from valence band to conduction band. So what will happen is that they will make a electron and hole pair. Electron and hole pair. Electron and hole pair. So this was the equilibrium concentration. This was the equilibrium concentration. But you disturbed the equilibrium. How you disturbed it? By throwing some light of having energy which is larger than the band gap. And because of that, some electrons got the enough energy to get excited from the valence band to conduction band. And they generated electron hole pair. The number of electrons generated and the number of holes generated are same, right? Electron and hole will be generated in pair. Here there was no electron hole pair initially. Like electron hole pairs were not there. These electrons are coming because of the donor atom, right? And some holes are coming because of thermal energy. Now because of this external energy as well, some electron hole pairs are generated. Now let's just say I know that initially I am having 10 to the power 16 and here I am having 10 to the power 4. Let's just say because of this energy, I know that extra 10 to the power 4 centimeter cube inverse electron hole pair will be generated. What I mean to say is that 10 to the power 16 were initially there, 10 to the power 4 were initially there. Now because of this light, here you can see that 3 electron and 3 hole pair are generated. So because of this light, I am saying that extra 10 to the power 4 centimeter cube inverse electron hole pair will be generated. Now this semiconductor knows that I am exposed to the light. This semiconductor knows that here I am exposed to the light. And since I am exposed to the light, I need to generate these 10 to the power 4 centimeter cube inverse electron hole pair. But the semiconductor will say that, sir, I am not going to generate it instantaneously. I will take some time, because you know that every system takes some time. This capacitor knows that it is exposed to 5 volt. But capacitor knows that I need to generate 5 volt. But capacitor will say that I need some time to generate 5 volt. Similarly, your fan will say that to run on 5 speed, I need some time. So similarly, this semiconductor also knows that I need to generate extra hole pair, right? Extra electron hole pair. So these are known as excess carrier. So I need to generate these excess carrier. So, but I will not do it instantaneously. I will take some time. So this excess carrier that I am calling as delta P, or you can call it as delta N as well, right? These were the thermal equilibrium carrier concentration. Now excess carriers are generated. So this you can call as delta P and this you can call as delta N, right? So this will be surely a function of time t. This will also be surely a function of time t, and both will be equal as well, because I know that electron hole pair will be generated. So both will be a function of time t. Now what may happen is that this intensity of light may decrease with respect to the length L. Basically, let's just say if I turn on this light, here, so the intensity of the light is maximum here, but as it is covering the distance, the intensity will keep on decreasing. So you are throwing the light here, but it might happen that the intensity of light keeps on decreasing. That means here there is maximum light, here there is lesser light, even lesser light. So intensity of light may decrease. It can decrease in any manner, or it might happen that it may not decrease, right? It might happen that you are throwing the light from all the side. From everywhere you are throwing the same intensity of light. So it might happen that it may not decrease. But we will take the worst case. We will take the case that the intensity of light may decrease with the distance. So these excess carrier concentration could be a function of x as well. So till this point, what did you understand? At equilibrium, we were having certain number of electrons and certain number of holes. Since it was n type, then the number of electrons were more than the number of holes. Then at x equals to 0, I throw some light. Since the light is having energy more than the band gap, then some electron hole pairs will be generated. Some electrons from the valence band will be getting enough energy to get excited into the conduction band, and electron hole pair will be generated. Both electrons, the number of electrons extra generated and the number of holes extra generated, both will be equal in amount, right? So number of electrons, excess number of electrons and excess number of holes, both will be equal in amount, right? Now these excess carrier concentration could be a function of time as well and could be a function of space as well. Why it could be a function of time? Because the semiconductor will not respond immediately. It may take some time to reach to the steady state. That means the steady state value is this much, that I need to generate 10 to the power 4 centimeter cube inverse in the electron hole pair. But how it will say that, sir, first I will generate one electron hole pair, then 2, then 3, then 5, then 7, then 10, then 10 to the power 2, then 10 to the power 3, and then 10 to the power 4. So it will take some time to reach. So it can be a function of time t. It can be a function of space x as well, because you are throwing the light at x equals to 0. So the intensity of light may decrease with respect to the length L. So it could be a function of space as well, and both will be equal in amount. So till this point, everything is clear to you or not? Everything is absolutely clear. And here you cannot apply the mass action law, because equilibrium is disturbed, right? Extra electron hole pairs are generated. In n-type semiconductor, you are expecting that these many electrons and holes will be there. But because of the light, extra electron hole pairs are generated. So the semiconductor is under non-equilibrium now. And that's why you cannot apply the mass action law here. Basically, previously what was the condition? N naught multiply with P n naught was equals to Ni square. But now what happened is that N naught has become, there are these many electrons, along with that these are the excess. So function of x and function of t, right? Multiply with, this is the sign of multiplication. P n naught was already there and excess these are generated. X t is equals to Ni square, which is not true, because N naught dot P n naught is equals to Ni square. So these are the excess guys, and these excess guys will not be that small. Okay, don't think that, sir, if this is 10 to the power 4, so this will be, sir, some 10 value or 10 to the power 1 value, then we can ignore it. You cannot ignore it. These will be pretty high value, because this light will be having more than enough energy to make a high number of electron hole pairs. Okay, so mass action law is not valid. Every theory is written. Okay, everything is written. My target was to explain you the concept, and that I have explained. Let's read out the theory, whatever that has been written. Okay, so in n-type semiconductor under thermal equilibrium, the electron concentration and hole concentration are Np naught and Pn naught. अरे भाई ये क्या लिख दिया, n n नॉट, राइट, n n नॉट, electron concentration in n type semiconductor at thermal equilibrium. So it will be n n naught. At x equals to 0 and t equals to 0. At time t equals to 0, what I am doing, the semiconductor is illuminated with the light of of photon energy is equals to h mu. The incident light generates additional electron hole pair within the semiconductor. Due to this optical excitation, the carrier concentration deviates from the equilibrium values. The intensity of light may decrease with respect to the distance. Therefore, the number of excess carrier also decreases as a function of distance, right? Hence, the excess carrier concentration becomes a function of position x. In addition, the generation of excess carriers does not occur instantaneously. When the light is switched on, the carrier concentration increases gradually. It needs to reach to 10 to the power 4, but it will reach gradually 10, 10 to the power 1, 10 to the power 2, and then 10 to the power 4. Passing through a transient state before reaching the steady state. This state is known as transient state, okay? Those who haven't studied network analysis, they would not know. This is known as transient state. Like when the fan is trying to go to the speed of 5, first it will go to speed 1, 2, 3, 4. So these 1, 2, 3, 4, this is known as transient state. And once it has reached to the steady state, that is the speed of 5. Okay, so this is your transient. Thus, the excess carrier concentration depends both on position and time, and it is expressed as delta n xt, excess electrons and excess hole, that is represented as delta p xt. Since each photon, this line is very important. Since each photon generates one electron along with one hole. What does that mean? That means this is the light. You are having a light of, let's just say, you are having a light which is having a power of 1 watt. You are having a light which is having a power of 1 watt. In this light, there could be a lot of power of 1 watt and energy of 1 joule. Okay, so this is the energy of one photon. Are you able to understand this point? So one photon will generate one electron hole pair. We will solve a numerical, it will be more clear to you. So basically, in one light source, there could be a lot of photon. In one light source only, there could be a lot of photon. So those photons, let us say there are 10 photons, then 10 electron hole pair will be generated. If there are 20 photons, then 20 electron hole pair will be generated. If there are 30 photons, then 30 electron hole pair will be generated. Okay. So in one light source, there could be a lot of photons. So one photon will generate one electron hole pair. And since they are generating electron hole pair, that means number of electrons and number of holes are equal. So delta nxt will be equal to delta pxt. All good? All fine? So now the total carrier concentration will be given by n n naught. Here what you need to write down, n n naught. Basically only need to change is n n naught. Number of electrons in n type semiconductor at thermal equilibrium plus delta nxt, and total, like did you understand what is this nxt? Nxt is that total carrier concentration, total hole, total electrons. This is your total free electrons, or I will directly write down total electrons, and this is your total holes. So equilibrium holes you are having, equilibrium electrons you are having, along with that excess electrons and excess holes. Okay. Now let's just say I have reached at the steady state. I have passed out the transient state. I have reached at the steady state. That means now these excess carriers, these excess electron and these excess holes will not be a function of time t. What I mean to say is that if this fan is running at a speed of 5, if the capacitor has got the 5 voltage, now the 5 voltage is fixed with respect to any time. If I turn on the fan at 1 p.m. and at 1.1 p.m. at 1 p.m. 1 minute, this is running at a speed of 5, then always it will run at a speed of 5 only until I make some changes. Until I again click on the button, until I make any changes, it will always run at 5 only. Are you able to understand this point? So if I am saying that I have reached to the steady state, that means these excess carriers will not be a function of time now. Now they have generated 10 to the power 4 electron hole pair. They have already generated 10 to the power 4 electron hole pair. So now they will not be a function of time. So at the steady state, what I can write down as delta nxt would be equals to delta nx, right? What I can write down, delta nxt would be equals to delta nx, and your delta pxt would be equals to delta px. Where? At the steady state. Because steady state has reached, that means you have reached out the maximum number of electron hole pair. Now these number of electron hole pair will not change. All clear? So all these scenario we will again understand with respect to different diagrams, so don't worry about that. So now at the steady state, the excess carrier concentration becomes constant with respect to time. So total carrier concentration are given by n naught plus delta nx and p n naught plus delta px. All good, all fine. You are not getting confused with the notation. Don't get confused with the notation. Now there is another point. Let the steady state excess electron hole pairs are 10 to the power 4 centimeter cube inverse. 10 to the power 4 centimeter cube inverse. So these many electron hole pairs you are generating at a steady state. So just let me know one thing. What will be the total carrier concentration at the steady state? What will be the total number of electrons at the steady state? So previously how many electrons you were having? 10 to the power 16 plus 10 to the power 4 nearly equals to 10 to the power 16 only, right? But what about the holes? I should have given the space, no? Where I would write down now. Not having any space, so I will have to adjust, but let's understand it. What about the holes? Holes initially was 10 to the power 4. Now extra 10 to the power holes are generated. What you can see? 2 into 10 to the power 4. So there is no significant change in the number of electrons, but there is very high change in the number of holes. What kind of semiconductor we are studying? N-type semiconductor. In N-type semiconductor, who are the majority? Electrons. So in N-type semiconductor, electrons are majority, and because of the lights, they are not getting changed much significantly. But the minority carrier concentration, which are holes, they are getting changed significantly. So what will be our matter of concern? Like who will change our current? If number of electrons, previously it was 10 to the power 16, now also it is 10 to the power 16 only. So will they generate any current? No, they will not generate any extra current. So who will be our matter of concern now? Matter of concern will be minority excess carriers. Say yes or no. Why minority excess carrier? Minority, what I am saying? Minority excess carrier. Excess carrier means delta pxt. And what do you mean by minority? Minority means holes in case of N-type semiconductor. And in case of P-type semiconductor, who will be the minority? Electrons. So our matter of concern will be shifted towards the minority excess carrier concentration. Minority holes. Excess means because of the light. So minority excess carrier concentration. Because minority excess carrier concentration are changing in a significant manner. Okay, all points are clear to you. Everything is very smooth, right? So this thing I have written here. In N-type semiconductor, let's shift it like this. Okay, all fine? Yeah, fine. In N-type semiconductor, the equilibrium electron hole concentration is already very high compared to the hole concentration. Equilibrium electron concentration is already very high compared to the hole concentration. Under non-equilibrium condition, the change in electron is relatively very small, whereas the change in number of holes is much more significant. Therefore, in this analysis, in the analysis of non-equilibrium behavior, greater emphasis will be placed on minority carriers, minority excess carrier, or you can say minority carriers. So our matter of concern will be more towards minority carriers. When the excess electron hole pairs are generated by illumination, the number is, so there is something called low level injection. What do you mean by low level injection? Let's just say initially I was having 10 to the power 16 number of electrons and number of holes were 10 to the power 4. Now I need to generate, now because of the light, these excess carriers are generated. Now these excess carriers should be less than 10 to the power 16. That means these excess carriers should not be too high that it will cross this value only. Are you able to understand this point? Let's just say I say that the excess carriers are generated are 10 to the power 20. Excess carriers that are generated are 10 to the power 20. So what will be the number of electrons? 10 to the power 16 plus 10 to the power 20. What that would be? 10 to the power 20. And what will be the number of holes? 10 to the power 4 plus 10 to the power 20. That would also be approximately 10 to the power 20 only. So this is known as high level injection. That you have thrown the light of so much high energy. The light is having so much of high energy that a lot of electron hole pairs are generated. And at very high energy, at very high temperature, or you can say at very high energy, what will happen is that I told you the semiconductor will start behaving like an intrinsic semiconductor. Where we studied that? In the second last lecture, right? So it will start behaving like an intrinsic semiconductor. You can see that 10 to the power 20, 10 to the power 20. So this analysis will never be asked. In your syllabus, low level injection is there. Okay. So only they will make sure that these excess carriers are lesser than the majority carrier concentration. So this is what is written. When excess electron hole pairs are generated by illumination, their number is smaller, not much smaller. It could be near to this as well. Okay. So their number is still smaller than the equilibrium concentration of majority carrier. This condition is known as low level injection. Okay. So always low level injection will be asked. That means the number of charge carriers, the number of excess charge carriers that are generated, the number of them will be lesser than the majority charge carriers. So this was your majority charge carrier, number was lesser than that. Here you can see that 10 to the power 4, 10 to the power 10, 10 to the power 4 and 10 to the power 4. And the excess charge carriers were 10 to the power 16, which were much lesser. So this is known as low level injection. So now based on whatever that we have studied, we will try to solve this question. This is not a problem, okay? This question will not be asked in the examination, but it will help you to clear your concept. Okay? So whatever that we have studied, based on that only this particular question is there. What they are saying? You should be able to understand whatever that is written. What they are saying? N-type semiconductor is given. Thermal equilibrium electron hole concentration is 10 to the power 16, 10 to the power 4. When everything was fine, this was the condition. Then what really happened? At t equals to 0 and x equals to 0. So this was your semiconductor at x equals to 0. Semiconductor could be having a length of L. So at x equals to 0 and at t equals to 0, you are throwing the light. And since you are throwing the light, you know that electron hole pair will be generated. Now these electron hole pairs will not be generated instantaneously, it will take some time. How much time it is taking? 5 microseconds. So steady state will be reached at 5 microseconds. And the excess electron hole pair that are generated, those are 10 to the power 4 at the steady state. Okay, at the steady state. Do you understand the meaning of at the steady state? That means excess carrier concentration, initially they started from 0, then 10 to the power 1, 10 to the power 2, 10 to the power 3, and then eventually they reach to 10 to the power 4. Okay, the excess hole concentration inside the semiconductor decreases exponentially with the distance x. Okay, what I am saying is that let's just say here you are having excess carrier concentration as 10 to the power 4. So with the distance, it will decrease exponentially. Is that clear to you? Are you able to understand what I am saying here? This they have given that this response will be exponential. It could be linear as well, or it might happen that it is constant as well. It could be exponential, it could be linear, it could be constant, it could be anything. But it is given that it is decreasing exponentially with the distance x. Are you able to understand what I am saying? So whatever that has been said in the question, is that clear to you? There was the semiconductor, N-type semiconductor was there, electron hole concentration was there, illuminated the light, because of that electron hole pairs are generated, steady state is reached at 5 microsecond. Okay. And in the semiconductor, the intensity of light would be decreasing. Here there is more intensity, but as you go ahead, the intensity of light would decrease, right? Because of that, the electron basically here there will be more electron hole pair generated, but here there will be less electron hole pair will be generated. So if the intensity of light is decreasing inside the semiconductor, that means the electron hole pair will also be decreasing, and that decrease is exponential. They have mentioned that in question. It could not be mentioned, it might be mentioned. So whatever that is mentioned, that you need to take. Okay. So you need to draw that total hole concentration versus x with respect to different time instants. That means at t equals to 1 second, at t equals to 3 second, at t equals to 5 microsecond, you need to draw the hole concentration with respect to x. And then what they are saying is that you are switching off the light at 7 microsecond. You are switching off the light at 7 microsecond. And the thermal equilibrium is restored at 12 microsecond. What is the meaning of that? First, what you did, you generated the light. You gave the light. Because of that, electron hole pairs were generated. So initially you were having some, this is again n naught. Okay. So n naught you were having. Because of that, some extra carrier came into action. Previously you were having p n naught and some extra carrier came into action. Now just as the light is gone, now what semiconductor will say? That I am not having any light. I am again under the thermal equilibrium condition. So these guys need to go now. Basically, you turned off the fan. You have turned off the fan. So fan will say that I was at 0, so I will move at the speed of 0 only. That means I will be at rest. In this question, when I remove the source, capacitor will say that what was my initial voltage? 0 volt. So I will go back to my 0 voltage. So now capacitor is trying to go to 0 voltage only. So similarly, what the semiconductor will say? That initially my electron hole concentration were this. Because of the light, these were generated. But now the light is gone, so you also will go. So we guys will also go. But they will not go instantaneously. If you turn off the fan will not turn off instantaneously. 5, 4, 3, 2, 1, 0. Similarly, capacitor discharging from 5 volt to 0 volt exponentially. Similarly, here as well, these 10 to the power 4 will not go instantaneously. They will also go exponentially. Is that clear to you or not? All good? All fine? So let's see what the question is saying and let's try to draw the waveforms. So you do it on your own in rough notebook. I need to take some break. I need to drink some water and then I will draw the waveform in this manner. The diagram has been made and better I should have written NP naught, PN naught. Sorry, N naught, number of electrons in N-type semiconductor, number of holes in N-type semiconductor, 0. And this is the steady state 10 to the power 4 centimeter cube inverse. We will draw at different time at 0 second, 1 second, 3 second, 5 seconds. So at 0 second also I will draw at 1 second. And what I need to draw? I need to draw the minority carrier concentration. Okay, minority carrier, hole concentration means minority carrier concentration. So total holes I need to draw. What will be your total hole? What will be the total number of holes? PXT, total number of holes will be equals to the equilibrium number of holes plus the excess holes that are generated, right? But these will be a function of time, these will be a function of space as well. But this guy is constant. So at t equals to 0, there was nothing. At t equals to 0, there was nothing. At t equals to 0 only, they turned on the light. So at that time, everything was fine. Everything was fine. So at that time, number of holes in N-type semiconductor at thermal equilibrium was 10 to the power 4. Just as the light turned on, these 10 to the power 4 got changed. Something will come into action here. In 1 microsecond, I don't know how much will be generated. I have no idea how much more holes will be generated, but I know that steady state will be reached at 5 microsecond. That means I know that these many excess holes will be generated at 5 microsecond. So at 1 microsecond, 10 to the power 4 will not be generated. Lesser than that will be generated. I am assuming that at 1 microsecond, 10 to the power 4 plus 100 more are generated. What I am saying, at 1 microsecond, 10 to the power 4 plus 100 more are generated. But where the intensity of the light is high? At x equals to 0. So these 10 to the power 2 are generated here. Basically, at 1 microsecond, initially you were already having 10 to the power 4. Now extra 10 to the power 2 are also generated. But these are generated at x equals to 0. Now what they are saying is that the intensity of light is decreasing inside the semiconductor. So hole concentration inside the semiconductor is decreasing exponentially. So this whole concentration will decrease exponentially. Are you able to understand this point or not? So this whole concentration will decrease exponentially and it will reach the thermal equilibrium value only. This thermal equilibrium value was 10 to the power 4. What I mean to say is that here there were more lights, so more electron hole pair were generated. So this I am saying that at 1 microsecond, this is the maximum number that is generated. What I am saying, at 1 microsecond, this is the maximum number that is generated. With respect to the distance x, it will decrease. Why so? Because here there is lesser light, here there is even lesser light, here there is even lesser light, or let's just say here there is no light at all. And if there is no light at all, then equilibrium will be maintained. So this concentration will decrease exponentially. Why exponentially? Because it is given. If it was given linearly, then it could have been linear as well. If it was saying that it is constant, that means whatever the number of holes are generated here, the same number of holes are generated here, same here, everywhere the same number of holes are generated. So it could be constant as well, or it could be linear as well, or it could be exponential as well. Depends on the given question. Okay. Well and good. Yeah, so next let's see at 3 microsecond. So at 3 microsecond, what will be the behavior? So at 3 microsecond, what I am saying is that already I was having 10 to the power 4. This much I was already having. Because of the light, 10 to the power 4 plus 10 to the power 3 is generated. 10 to the power 4 plus 10 to the power 3 generated, but the maximum will be generated at x equals to 0. Why is that so? Because with respect to the distance, the intensity of light is decreasing, so the carrier concentration will also decrease. The whole concentration will also decrease in this manner. And it might happen that at some point the light is not even reaching, so concentration will be nearly 0. The excess carrier concentration will be nearly 0, but whatever that you are having previously, basically this guy is not changing. This guy is saying that I will not change. Now only change will be done in this particular value, right? Now I know that steady state is reached at 5 microseconds. So I am pretty sure that at 5 microsecond, 10 to the power 4 plus 10 to the power 4 will be generated, because this is the steady state. This is the steady state condition. So 2 into 10 to the power 4 centimeter cube inverse. So this is the steady state condition, and after that it will decrease exponentially with respect to the distance. So this is the diagram we are drawing with respect to the distance. Is that clear to you? Okay. Now at 7 microsecond, what you were doing? At 7 microsecond, the light was turned off. At 7 microsecond, the light was turned off. So at 7 microsecond as well, the same condition was there, right? At 7 microsecond as well, just before 7 microsecond, I am talking about 6.9999 microsecond. At 6.99 microsecond as well, the number of holes cannot be generated more. Previously, the number of holes were 10 to the power 4. Because of the light, more 10 to the power 4 were generated. So now more cannot be generated. 2 into 10 to the power 4 is constant now. That will not increase. So at 7 microsecond as well, the same diagram you will get, because the effect of light will come into action after 7 microsecond. Are you able to understand this point? Right? So this is how the same graph will go. Basically at x equals to 0, you would be having 2 into 10 to the power 4 only. Make sure that you notice this, we are drawing with respect to x. That means this is our semiconductor. We are drawing with respect to the semiconductor, with respect to the distance x. We are not drawing with respect to the time. With respect to the time as well, we will draw the graph, but that graph will be different. This we are drawing with respect to x. Where the effect of time is coming into action? Here. Initially, at time t equals to 0, there was nothing. At time t equals to 1 microsecond, 10 to the power 2 came into action. At t equals to 3 microsecond, 10 to the power 3 is coming into action. At t equals to 5 microsecond, 10 to the power 4 is coming into action. At t equals to 7 microsecond, 10 to the power 4 remains constant, right? And at t equals to 9 microsecond, what will happen? Now the light is gone. Since the light is gone, so what will happen? The semiconductor will say that whatever the extra that you have generated, I don't want that extra, because the light source is gone, no? And since the light source is gone, the semiconductor will say that whatever that you have extra generated, reduce that to 0. So already I was having 10 to the power 4. This was the already value that I was having. Let's just say your capacitor is already, this I cannot explain with the example of capacitor, because capacitor will completely discharge, but just understand with respect to your semiconductor only, because semiconductor is having that this much number of charge carriers I am already having. Now the extra that you have generated, that should be erased. So extra 10 to the power 4 we have generated, and light was turned off at 7 microsecond. So between 7 microsecond to 9 microsecond, there has been a gap of 2 microsecond. And since there is a gap of 2 microsecond, so in 2 microsecond, the charge carriers would have decreased. So from 10 to the power 4, let's just say I am saying that we have went to 10 to the power 2. What will be the value? That I don't know. It will be a rough value. It is just a rough value that we are putting. Then at 11 microsecond, next at 11 or 13, next at 12, and 12 is the steady state, right? 12 is the steady state, 7, 9, and next directly at 12. So at 12 as well you are getting the steady state, no? What they are saying, the thermal equilibrium is restored at t equals to 12 microsecond. What does that mean? That means whatever the extra was generated, those are gone. Whatever the extra was generated, those were gone. So this is your thermal equilibrium that has been generated at t equals to 12 microsecond. Is that clear to you or not? I hope this whole process is clear to you. A very, very typical process, but with respect to diagram, if you are understanding, the important part to understand here is that this whole concentration is a function of x as well, it is a function of t as well. That we have already understood. Then I got to know that at t equals to 0, I am turning on the light. So initially there was 10 to the power 4, those are there. Now since there is a transient, so it will take some time to reach to 10 to the power 4 centimeter cube inverse carrier concentration. So in 1 microsecond it would have reached 10 to the power 2. In 2 microseconds it would have reached 10 to the power 3. In 5 microseconds it would have reached the steady state, that is 10 to the power 4, right? So this would be the total carrier concentration. Here excess carrier concentration is also there, and your minority thermal equilibrium concentration is also there. So what this was known as, this much value was known as delta Px. Why I'm not writing down the function of here? What I will write down? Here I will write down delta Px3. Why delta Px3? Because these are the excess holes generated till 3 seconds. These are the excess holes generated till 5 seconds. But I know that more than this will not be there. So here also I can write down the same thing, no? Excess holes generated till 7 seconds or 5 seconds. So that would be equals to delta Px only. And already you are having 10 to the power 4. Is that clear to you? Already you are having 10 to the power 4. So excess carriers that are generated at the steady state, those are delta Px, and that is equals to 10 to the power 4. And now what really happened? These guys started decreasing because light is gone. Here at 7 microsecond light is gone. So semiconductor will say that I want to reach to my thermal equilibrium. That means I want to reach to this value. So you are having 2 into 10 to the power 4. Semiconductor will say that reduce it to 10 to the power 4 again. So reducing and then finally completely reduced. Is that flow clear to you? Now you need to draw the diagram of Pxt with respect to x and with respect to t in 3D. Okay. So we are going to draw this diagram in 3D. Keep your full concentration, then only you will be able to understand. On x-axis, what is there? Hole concentration. On y-axis there is hole concentration. On this is the distance. That means this is your semiconductor. This is x equals to 0, x equals to L. You are throwing the light at t equals to 0. You are throwing the light at t equals to t1. Okay. The light has been thrown at t equals to t1. Okay. And steady state is reached. Steady state reached at t equals to 0. Steady state is reached at t equals to 0. You are drawing the whole concentration with respect to time and with respect to the distance. So forget about the distance. First, only focus on the time. Okay. So whole concentration. So initially, what was the whole concentration you are already having? That was equals to number of holes in n-type semiconductor at thermal equilibrium. So that was your Pn naught. Okay. Now the light turned on at t equals to t1. So let's just say this is the time where the light was turned on. This is the 3D diagram. You are focusing on these two guys. All these are 90 degree. Okay. These angles are 90 degree. I hope you know what is 3D. So all these are 90 degree. They are basically, this is the graph we are doing. Whole versus time. Okay. So now what is happening? Till t equals to t1. Till t equals to t1 there was nothing. Till t equals to t1 there was nothing. Just as at t equals to t1 the light is falling. If the light is falling, then what will happen? The number of hole concentration, the number of holes, the number of excess carriers, they will start increasing. They will start increasing, right? They will start increasing. They need to reach to 10 to the power 4 value, but they will take some time. They will take some time and then they will reach here to this value at t equals to 0. Is that clear to you? Now what this will be known as? This was your Pn naught and this will be known as your delta Px. So total number of holes at thermal equilibrium, sorry, not thermal equilibrium, very sorry, the word is wrong. Total number of holes at steady state. What is Px? Total number of holes at steady state. Total number of holes at steady state. that will be called as delta, not delta px, only px, and that would be equals to initially p n naught that you are having plus the excess carrier that you have generated, and now this will not change with respect to the time, right? So can I draw at the steady state what this will be known as? This condition will be known as steady state. So what I am doing, I am drawing the whole concentration with respect to x at steady state. If I am in this plane, if I am in this particular plane, whole concentration versus distance, if I am there in this particular plane, whole concentration versus distance, if I am in this particular plane, that means I have reached to t equals to 0. Let us say if I am here, that means I am there at some t equals to t2. This is not my steady state. Where is my steady state? My steady state is at t equals to 0. So if I am on this particular plane, if I am moving on this particular plane, that means I have reached to my steady state. And yes, I have reached to the steady state. T equals to 0 is a steady state. Now what I am doing is that I am drawing whole concentration with respect to the distance x. That means when you go inside the semiconductor, the intensity of light may decrease. The intensity of light may be decreasing, right? So the whole concentration with respect to the distance may be decreasing. So what kind of graph you will be getting? This kind of graph you will be getting. But make sure that only the excess carrier will be gone. These carriers, only the excess carrier will be gone. These are the thermal equilibrium carriers. They will remain there for sure. They will remain there for sure. Because these were the initial whole concentration that you were having in n-type semiconductor. So did you understand this graph or not? In 3D, a very good graph, just it is giving you the complete concept of whatever that we have discussed in last 1 hour. Whole concentration versus time versus distance. Okay, this time is increasing from here, t1 to 0. T1 time is some negative time. Let's just say t1 is minus 5 microsecond. At minus 5 microsecond, you just turned on the light. The light concentrate. If you just turn on the light, then the whole concentration will not increase instantaneously. It will take some time. Already you are having this much concentration, which was your equilibrium whole concentration, right? Now the whole concentration started increasing. The whole concentration started increasing. This value, the value started increasing. You know that in whole concentration we are moving upward. So value started increasing. But at the t equals to 0, we have reached to the maximum value. That is known as delta px. So after that, if I don't remove the light, this concentration will remain the same. What I am saying is that if I don't remove the light, then this concentration will remain the same. It will remain the same if I don't remove the light. And this graph will keep on going. This red graph that I have drawn, this graph will keep on going like this. This graph will keep on going like this. In 3D, we are drawing the graph. I hope you are able to catch up. So this graph will keep on going like this at all the temperatures. Sorry, at all the time, not temperature, sorry, at all the time, because after that steady state is maintained, right? And now when I am drawing the graph, how I am drawing this particular graph? How I am drawing this particular graph? Because I am assuming that the concentration is decreasing exponentially. The intensity of the light is decreasing in the semiconductor, so the concentration is decreasing exponentially. So this is what I am assuming, and this is how I have drawn the graph. And this graph is drawn at steady state. So this is the point of steady state. This is the point of steady state. Can I draw this graph without the steady state as well? What I mean to say is that the same kind of graph I can draw here as well. The same kind of graph, like starting from here, just a rough diagram I am making, starting from here, and this is how it will go. Starting from here, and this is how it will go, and this value is equals to delta Pn not only. What I mean to say is that from this plane, what I am picking, this is the bottom of the plane. This is the bottom of the plane, and from here you know that whole concentration is Pn naught, that is constant. This is the constant value, and I am drawing the graph at t equals to t2. At t equals to t2, I know that delta px is not achieved. That means 10 to the power 4 centimeter cube inverse is not achieved. Some 10 to the power 3 centimeter cube would have achieved. So total concentration is this value, which is this, plus some other value, which is this. So your graph will be starting from here, but eventually with respect to the distance, it will decrease. Is that clear to you? Mostly in textbook what you would find, or in the lectures what you would find, is that always people will draw only this steady state graph. So people don't even understand that it could be a function of time as well. Are you able to understand this point? So is everything is clear to you? That the excess hole concentration is a function of time and a function of space as well. But this function of space is not fixed. What I mean to say is that it could be constant or it could be linear as well. So you are not sure what kind of profile will be given. So it could be exponential, linear or constant. What I am saying, constant, linear or exponential. So by default it could be anything, sorry, it could be anything, but this is your by default, by default. So most probably it will be mentioned in the examination that how the concentration of how the concentration of excess charge carriers are decreasing. But this will be surely exponential. What I am saying, another new point I am telling, the excess carrier concentration that is decreasing with, that is increasing with respect to the time, this will be surely exponential, surely exponential. Is that clear to you? Okay, so this particular diagram will be surely exponential. Now if I say that at t equals to 0 I have turned off the light, what I am saying, steady state is reached at t equals to 0 and at t equals to 0 I have turned off the light now, then what will happen? The semiconductor will say that I will lose everything. What semiconductor will say, that whatever that you have given me, whatever this concentration that you have given me, I will lose it completely. I will lose it completely. अरे भाई क्या दिक्कत है? Just I am showing this is how it will lose it completely and it will again reach at Pn naught. So let me try to draw the diagram in a better manner. It will be very much let me copy it. Okay, let me copy it, and then what I would do is that I would remove all these and I will try to draw it again. Yeah, so this was our diagram. Now what I am saying is that light source is removed at t equals to 0. So whatever the light source was there, that is removed at t equals to 0. So semiconductor will say that whatever the excess carrier that I have generated, those excess carriers should be gone. I don't want these excess carrier, whatever the excess carrier you are having at steady state, whatever this 10 to the power 4 value that you are having, those value I don't want. So these values will be gone. So these values will be gone, and eventually at some time at the steady state, what it will do is that it will reach to its equilibrium value, that is Pn naught. Okay, so this is the diagram with respect to the time. This is the diagram with respect to the time. With respect to the time. Okay, and if I want to include the distance as well, at steady state only I am drawing the graph. This was your steady state. So at steady state, this kind of a graph you got. What kind of graph you got? You know that at steady state the concentration may start decreasing with respect to the distance. So here this is the steady state, here you are having the maximum concentration, but the excess carrier concentration may be start decreasing with respect to the distance x. And why it is decreasing? Because the intensity of light may decrease with respect to the distance x. So I said that this will be surely exponential. So I am saying that this will also be surely exponential. Are you able to understand what I am saying? This graph, whatever the graph that you are getting with respect to the time, that will be surely exponential. But whatever the graph that you are getting with respect to the distance, that could be exponential or linear or constant as well, whatever the nature is given. Is that clear to you? But the graph with respect to time will be surely exponential. Is that clear to you? Now, if I need to write down the value of hole concentration with respect to the time, if I need to write down PT, not PT, I am just writing down delta PT. What does that mean? That how your excess carrier concentration is changing with respect to the time. Are you able to understand this point? What I am saying? How your excess carrier concentration is changing with respect to the time. If you need to write down the capacitor charging equation, how do you write down? Sir, 5 into 1 minus e to the power minus t by 2. Sir, eventually it will try to reach to 5 volt. So eventually, sir, it will try to reach to delta px going through a transient. So 1 minus e to the power minus t by 2. Here I will write down tau p. This tau p is known as carrier lifetime. And what is this carrier lifetime? We will discuss. So this tau p is known as carrier lifetime. But this will be the true equation if a switch is turned on at t equals to 0. If switch is turned on at t equals to t1, then what will be the equation? This will be the equation, right? So here I will write down the equation in this manner because I know that the switch is turned on at t equals to t1 divided by tau p. Okay, don't try to mug up the equation, just try to understand it, and when we solve the problem it will be all clear to you. Don't worry about that. Okay, sir, how this equation came, you don't need to worry. You don't need to worry about the derivation. And what if the light source is removed at t equals to 0? The light source is removed at t equals to 0. So whatever the delta px that you are having, that will decay down. So what I am writing, the excess carrier concentration with respect to the time. So what that would be? Sir, whatever the delta px that I was having, sir, whatever the 5 volt that I was having, that will be exponentially decaying. So whatever the delta px that I am having, whatever the delta px that I am having, that will also exponentially decay. But what if the light source is turned off at some t equals to t2? Here the light source is turned off at t equals to 0. But what if it is turned off at some t equals to t2? So what you will write down? T minus some other value divided by tau p. Considering that light source is turned off, light turned off at t equals to t2. Very simple thing. When you solve the problem, everything will be clear to you. Okay, don't worry about that. When you solve the questions, every single thing will be absolutely clear to you. Okay, all clear? So at t equals to t1, the light was turned on. The target was to reach to this delta px value. The target was to reach to this 10 to the power 4 value. Okay, so I need to generate excess carrier concentration of 10 to the power 4. So 10 to the power 4 is my final value. So 10 to the power 4, 1 minus e to the power minus t by tau p. What is this tau p? That I will tell you. Okay, so whatever the time it takes, in that manner you can tell. Okay, and let's just say the switch was turned on at t equals to t1. So this is what I will be writing. These equations are coming from the transient part. You know how to write down the equation of transient. So from there you can write down these equations. And if the switch is turned off, that means if the light is turned off, what does that mean? That means whatever the excess carrier concentration that you are having, that will decrease exponentially. So if that is decreasing exponentially, so whatever this 10 to the power 4 that I am having, that will decay down. So 10 to the power 4 e to the power minus t by 2. But let's just say this switch was turned off at t2. So t minus t2 by 2. All clear? Okay. So these response will be surely exponential. But here I am not writing down any equation. Here I am not writing down any equation. That I am not writing down any equation like this. So delta px e to the power minus x by diffusion length. This LP is known as diffusion length. What is this diffusion length? That also I will tell you. But this equation I am not writing down for this one because it is not certain. It could be some different as well. It could be linear as well. So what it would be? Delta px into 1 minus x by LP. This kind of equation could also be there. Or simply delta px. That means whatever the excess carrier concentration that you have made, that will remain the same, or it could be linear, or it could be exponential. So this will be the equation for exponential, this will be the equation for linear, and this will be the expression for uniform, right? So that's why we are not writing down any particular equation for the excess carrier concentration with respect to x, but we can write down the equation for excess carrier concentration with respect to the time. Excess carrier concentration with respect to time we can write down, but excess carrier concentration with respect to x, we are not writing down any equation. Okay, it could be anything. So here I am writing down, it could be anything. So with respect to x, how I should write down? Oh, let's not write down. Okay, let's not write down the equation. All good. Concept is clear to you. Forget about the equation, forget about anything. Concept should be clear. That is clear to you, right? Now we need to see the definition of a minority carrier lifetime. Then I said that there is something called diffusion length as well. So let's see the definition of these two things. So I told you that from the conduction band, electron will go to the, from the valence band, electron will go to the conduction band, right? Making a hole. Now it will stay there for some time and then it will recombine with the hole. This is known as, whatever the time it was staying here, that time is known as minority carrier lifetime. The electron was generated, electron hole pair was generated, then it remained there for some time. Whatever the time it was left, the average time is known as carrier lifetime. Are you able to understand this point? So before recombining, whatever the time the electron in the conduction band is spending, that time is known as minority carrier lifetime. Why it is written as minority carrier lifetime? What does that mean? That means we are relating with respect to this example. How I am relating? That here light was turned off. Now if light is turned off, that means whatever the excess carrier that was generated, whatever the excess electron hole pairs that were generated, just as the light is turned off, what will happen is that they will say that now your time is up, you need to go, right? What semiconductor will say, just as the light is turned off, semiconductor will say that there is no light source, I need the thermal equilibrium condition. So they were generated because of the light. Now they know that they have to die, right? This have to destroy it, this have to be destroyed, this electron and hole needs to recombine. So whatever the time they are spending before recombining, this particular time, whatever the time they are spending before recombining, that is known as minority carrier lifetime. Is that clear to you or not? So minority carrier lifetime is defined with respect to this condition. First I gave the general condition, that what do you mean by lifetime? So there was an electron, there was a hole. So electron hole pair was generated. Now electron needs to recombine with the hole. So whatever the time that electron is spending there, that is known as lifetime. Now talking about the minority carrier lifetime. So just as the light is turned off, what will happen is that the electron and hole needs to recombine now. Whatever the excess carrier that was generated, that needs to be destroyed. And if you need these electron hole pair to be destroyed, then electron and hole pairs should be recombining. Electron and hole should be recombining. So after the light is turned off, how much average time they are spending, that average time is known as minority carrier lifetime. Okay, some electron will be spending more time, some electron will be spending less time, some electrons will be spending some time in between. So whatever the average time they are spending, that time is known as minority carrier lifetime. Okay, so the minority carrier lifetime is the average time and excess minority carrier exists before it recombines. Electron in p type, hole in n type. Minority carrier you understood, right? Because we focus more on minority carrier only. So electrons will be minority in p type and holes will be minority in n type, right? The physical meaning is it measures how long excess minority carriers survive under non-equilibrium condition. So whenever there was non-equilibrium condition, this was the equilibrium condition, this was your equilibrium condition, this was also your equilibrium condition, here also you have reached to the equilibrium condition. But in this non-equilibrium condition, when there was light, light was removed, so electron hole pair were generated. So for how much time they actually survived there? So the average time is known as minority carrier lifetime. And what is this diffusion length? The diffusion length is associated with the distance. So now what will happen is that here the concentration is more, here the minority carrier concentration is more, and here the minority carrier concentration is less. So minority carrier concentration are actually diffusing. So the average length that they are covering. So the definition is written that diffusion length is the average distance an excess minority carrier travels by diffusion before it recombines. Okay, so here what do you see is that here the excess carriers are more, but here the excess carrier are less. That means here the excess carrier has been recombined. So this is what it means, whatever the average distance it is covering. Going from here to here, whatever the average distance your electron hole pair are covering. Basically what is the scenario is that just as you throw the light, there will be more electrons here because the light has been thrown here, and there will be lesser electrons here. So whatever the average distance that they are covering, electron hole, electron hole, electron hole. So whatever the average distance that they cover, that is known as diffusion length. The formula is important. The definition, everything is not important. So there is a relation between minority carrier lifetime, diffusion length and diffusivity. That is known as L equals to under root d tau. How do I remember it? La, do, tofi. Okay, these are the words in Hindi. La, do, tofi. How do I remember? La, do, sorry, la means L. La, do, tofi. Like give me toffee. This is what I am saying. Toffee means candy. So la do toffee. If you are someone who can understand Hindi, then you can make this trick. La do toffee. Otherwise you will be forgetting it. Do you remember that formula? D equals to mu into Vt. How did I tell you to remember? A, B, C, D, U, V. Right? So if you don't make any trick, then you will be forgetting it. You will be doing sir, that's a D I will be putting here, Vt I will be putting here. Those error you will do. And here also if you don't remember the formula, you will be making the error like sir D equals to under root L2. So these kind of things you will be doing. So how will you remember? Sir, la, do, toffee. Give me toffee. This is tau, D, L. Lifetime is shown by tau. Diffusion length is shown by L. So la, do, toffee. L equals to under root d tau. Okay. So this formula, along with that there is another formula. What is that? D equals to, this formula also you should not be forgetting. D equals to UV. So mu into Vt. D is the diffusivity, tau is the minority carrier lifetime, and L is the diffusion length. Okay, everything is clear. Even if the definition is not clear, don't worry about that. Formula are important. For solving the problem, formula are important. But you understood the minority carrier lifetime. What is the minority carrier lifetime? The average time it is spending before recombining. And what is the diffusion length? The average time it is spending before recombining. Sorry, the average length it is covering before recombining. So diffusion length is associated with the length and diffusion time is associated with the time. Okay, so what is your diffusion length? Diffusion length, here there are more minority carrier, here there are lesser minority carrier. So whatever the length they are covering before recombining, that length is known as diffusion length. Okay, so this is the formula that they have written. D is the diffusion coefficient, or you can call it diffusivity of minority carrier. Tau is the minority carrier lifetime. And what is the physical meaning? It tells how far excess minority carrier can move in the semiconductor under non-equilibrium condition before they disappear. So here the minority carrier concentration has been, excess minority carrier concentration has disappeared. Here there is minority carrier concentration. That means here there are holes, but whatever the excess that was generated, that is gone. Okay, all fine. If you feel like that sir it is too much, then it is not actually too much. I am just explaining too much, I guess. Don't feel like that sir there are a lot of things, how will I remember? Very simple analogy I have given just by the capacitor example. So you will be able to solve the problem in the easiest manner, that is my guarantee. Okay, so just cover whatever that I am telling, and that would be more than enough to go. So this formula and this formula, that these two formula till this point we have understood. Now I need to take some break, and then we will be studying about generation rate and recombination rate. Very simple thing. Electron hole pair are generating. So with what rate they are generating, that is known as generation rate, and with what rate they are recombining, that is known as recombination rate. So the rate of electron hole pair being generated per unit volume per unit time, that is known as generation rate. What will be the unit? Per unit volume per unit time. So let's just say 10 to the power 14 electron hole pair were generated per unit volume per unit time. Okay, generation rate and recombination rate with the rate that they are recombining. So that is known as recombination rate. Now what is the formula of recombination rate? Very, very important. The most important thing of this whole chapter. So that we will see after a break. Let me take some break. Let me drink some water, and then I will come back. Okay. Yeah. Yeah, welcome back guys. So we were studying about generation rate and recombination rate. So number of excess charge carriers generated per unit volume per unit time was generation rate, and the charge carriers number of charge carriers recombining per unit volume per unit time was recombination rate. Okay, so we were majorly focused on excess charge carriers because when you are illuminating the light, excess charge carriers are being generated, right? So your recombination rate, this is a very important formula. So your recombination rate will be proportional to excess charge carriers. Say yes or no. Excess charge carriers. Say yes or no. Right? And it could be a function of both space and time. Why is that so? Because excess charge carriers can be a function of space and time. Excess charge carriers are both the function of space and time. That's why recombination rate can also be a function of space and time, right? So when you remove this proportionality sign, what you will get? Now, let's just say there is n-type semiconductor. So in n-type semiconductors, charge carriers will be both electrons and hole, because excess charge carriers will be generated in electron hole pairs, right? Whatever the excess charge carriers that are holes generated, same number of electrons will also be generated. But what we focus on? We majorly focus on the minority, right? In n-type semiconductor, I will focus on delta P. Although the same delta N is also generated, but my focus will be on delta P, right? So when I'm writing down the formula, at that time I will be writing down delta P x T for n-type semiconductor. Are you able to understand this point? If I am saying that in n-type semiconductor, excess charge carriers generated are holes, which are delta P x T. So can you tell me how much excess charge carriers generated, which are electrons? What is the amount of that? That amount will be similar to the holes only, because excess charge carriers are generated in electron hole pair. So if I know how much holes are generated, then I know that how much electrons are also generated. But whenever you write down the formula of recombination rate, you focus on minority excess charge carriers. What I'm saying? Minority excess charge carriers. Excess means which are generated because of the light. Minority means holes. So this I am saying for n type. But don't confuse yourself saying that sir, delta P and delta N will be different. No, they will be same only. But when we write down the formula, we focus on the minority excess charge carriers. Is that okay for you? So this is the formula for recombination rate for n type. And when you remove the proportionality sign, what you get? When I remove the proportionality sign, I will get 1 by tau p. So when I remove the proportionality sign, I get 1 by tau p. And it is pretty obvious as well. Why is that so? Because if tau p is high, if your lifetime is high, that means you are recombining slowly. If lifetime is high, then electron hole pairs are recombining slowly. So this particular formula that I have derived, or you can say just I have simply put down with the condition that tau p is a constant. It is not a function of space and time. Because you are saying that recombination rate, here I should have written Rxt, right? Because you are saying that recombination rate is a function of, let's write down the formula again, Rxt. Recombination rate is a function of x and t, and that is proportional to excess charge carriers, which is a function of x and t, right? So you are removing the proportionality sign, so you are getting something called 1 by tau p. So this tau p has to be a constant and uniform. That means it should not be depending on time, or it should not be depending on space. Is that clear to you or not? So here what I'm writing down, tau p is constant and uniform. It should not be depending on x, it should not be depending on time t. Is that okay for you or not? So this I have written for n type. Similarly for p type, what will be my formula? Similarly for p type. In p type, I will be focused on the minority charge carriers. Minority excess charge carriers. Who will be minority excess charge carriers? Those will be holes, right? So formula for recombination rate in p type, recombination rate in n type, recombination rate in p type. So minority excess charge carriers, there will be electrons. Although the number of electrons will be equal to number of holes only, but those will be electrons. And divided by tau n. What is tau n? Lifetime of lifetime of electrons, and tau p is lifetime of holes. So this formula is very, very important, but along with that there is this condition important as well, that your tau should be constant and uniform. So this particular formula which every student remembers, that sir, Rx is equals to delta P by tau P, and sir Rx is equals to, or Rx you can call R and Rp, whatever you want to call, basically excess minority carrier concentration divided by the lifetime. So this formula you will be able to remember, but this is applicable only when your tau P is constant and uniform. And at the steady state, what will happen? The recombination rate will be only a function of x, right? The recombination rate will only be a function of x. Why is that so? Because time term will be gone, because you are at the steady state now. Now your carrier concentration is not changing with respect to x. So your carrier concentration, your excess carrier concentration has been fixed. Or you can write down the formula as this as well. So people usually remember this formula. They don't even consider that delta P could be a function of t as well. So actual formula is this, but this formula is applicable at the steady state. Again, it is applicable for the condition that your tau is constant and uniform. In all the questions till this date in GATE examination, tau has been always constant and uniform, but there was one question in GATE 2022 examination, they did not mention about the lifetime. So there everything is changing. So I will solve that particular question. Till this date, everywhere the solution is wrong for that GATE 2022 examination problem. Excellent problem it was. Okay. So although they get the answer, but luckily they are getting the answer. So we are going to discuss that particular question in great detail. So very, very important condition that tau should be constant and uniform. Tau will be constant for sure. Constant means it should not be depending on time. So tau itself is a time. Lifetime itself is a time only. So how it will be depending on time, right? But it cannot be uniform all the time. It can be depending on x. Basically, as you go into the semiconductor, as you move into the semiconductor, your lifetime may be changing. Your lifetime will surely be constant, no? Why it is constant? Because time itself is a time only. Lifetime itself is a time. So it will never depend on the time, but it can depend on the distance. As you walk, as you move into the semiconductor, your carrier lifetime may change. So this is very important condition that you will apply this formula only when your carrier lifetime is uniform. It will be surely constant, so it is pretty obvious. You don't even need to write down that it should be constant. It will be surely constant, but it should be uniform as well. So again I am repeating, very, very important formula. Like your 90% of the GATE question will be solved by this particular formula only. That's it. Only using this formula, your 90% of the GATE problems will be solved from this particular topic. What is that formula? The recombination rate is equals to excess minority carrier concentration divided by their lifetime. Excess minority carrier concentration or excess charge concentration, I should write down. Excess charge carrier concentration, excess charge carrier concentration. So excess charge carrier concentration divided by their lifetime. All good? All fine? Okay. Let's move to our next topic, that is continuity equation. So everything that we were studying, only we were studying for this particular thing, continuity equation. So usually this topic is started from this particular slide, but last 1 hour and 30 minutes we were discussing just to write down the equation in a good manner. So what does the continuity equation tells? So continuity equation, even mechanical engineering will be studying, civil engineer student will also be studying. Continuity means whatever that is coming, that will flow out. That's it. That means things will be conserved. Let's just say, or forget about any analogy, here only you will be able to understand. So let's just say this was my semiconductor. I am calling this as p-type semiconductor. Okay, this is my p-type semiconductor. In this p-type semiconductor, I am throwing some light. Because of this light, what will happen? The minority carrier concentration will be increased. Like majority will also be increased. What I mean to say is that holes will also be increased, but electrons will be also increased, right? And we will be focusing on the minority carrier concentration. So there will be change in the concentration of electron. So change in the concentration of electron with respect to time. So this is change in the concentration of electron per unit volume per unit time, because concentration is always given in centimeter cube inverse. So concentration of electron per unit volume per unit time. So change in the concentration of electron per unit volume per unit time would be equals to generation rate minus recombination rate. Why is that so? Because generation rate means excess carriers are generated. Recombination rate means they are being recombined. So generation minus recombination will be equals to whatever that is effectively left. Along with that, one more term will come. 1 by q jnx 1 by q djnx by dx. Why that so? Because of the current as well. No, if the current outflowing is more, if the current flowing out is more and current flowing in is lesser, then the number of electrons will be getting increased inside the small volume. So this we have already seen. So for the electrons, what we use the positive sign. This is your continuity equation, and you go and check out the step for getting this final answer. For getting this final answer, you will have to go through a very high level of mathematics. Not very high level of mathematics, that means basically a lot of mathematical calculation you need to do. Then only you get to this final expression. But without even doing any mathematics, we are writing down this final expression. Generation rate, number of charge carriers being generated, and recombination rate, number of charge carriers being destroyed. So total charge carriers that are being generated, will be given by generation rate minus recombination rate. But one more phenomena is there, that is the current. If current flowing out is more and current flowing in is less, that means the electrons getting in is more and electrons getting out is less. That means the concentration of electron is getting increased inside this small volume. So plus 1 by q djx by dx. So this is the continuity equation for electrons in p-type semiconductor, because we will be focusing on minority carrier concentration. Why we are focusing on minority carrier concentration? Because minority carrier concentration is getting changed significantly, but majority carrier concentration is not changing that much. Is that clear to you or not? Is this equation clear to you or not? So this is written for the p-type. Similarly, you can write down for the n-type as well. So complete theory I have already written down here. So for electrons, the continuity equation for the electrons will be delta n by delta t plus 1 by q delta jn by del x plus generation rate minus recombination rate. Here I have given the complete formula that it will be depending on x and t, and it will be depending on space only, right? Now delta n by delta t is rate of change of electron concentration with respect to time, and here the definition is also given. What is the definition? Definition says that it is based on the principle of conservation of charge. Okay, so whatever that is going in, that should go out, right? So the rate of increase of carrier concentration per unit volume, that would be equals to net inflow of charge carriers per unit volume plus generation rate minus recombination rate. Net inflow, generation rate minus recombination rate. And for the case of holes, there will be a negative sign here, right? You can see there has been a negative sign. It has been written minus 1 by q djpx by dx plus generation rate minus recombination rate. And why this negative sign, you already know, right? In detail we have done the explanation. Now you are able to understand that why we focus so much on 1 by q dj by dx. So the reason was this continuity equation. Now you are able to understand continuity equation in a very easy manner, right? What is 1 by q djx by dx, that we already know. Generation rate, recombination we already know, and generation rate minus recombination rate is showing the net generation of the electron. That means whatever the electrons that are being generated minus those are recombined, so that would be the net electrons that are generated. All good, all fine. So for both of the cases you are able to write down the continuity equation. Let's see some special cases. So under steady state, what is the meaning of steady state? The meaning of steady state is that now your excess charge carriers are not changing. So what does that mean? Here I wrote down that what will be the number of electrons? That will be the number of electrons in p-type semiconductor at thermal equilibrium plus excess electrons plus excess electron. So these are your number of electrons. This is this n that I have put here. This n is this one. So this value is already constant. Np naught is already constant. Now if I say steady state, what is the meaning of steady state? That means this value also has reached to its maximum. That means if excess charge carriers generated should be 10 to the power 4. So now we have reached to the 10 to the power 4. Now your delta n will not change with respect to the time. Your delta n is also constant. So at the steady state, if I do dn by dt, what that would be? That would be equal to 0, right? Steady state means electron concentration is, or minority carrier concentration is not changing with respect to the time. So minority carrier concentration is not changing with respect to the time. So delta n by dt I am directly putting. That means the concentration with respect to time is not changing. Electric field is 0 and your carrier profile is constant. The other name of this carrier profile is, if I say carrier profile is constant, what does it means? That means there is uniform illumination. What is the meaning of uniform illumination? That means from all the side light is coming. Here, 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 from here, here, here as well light is coming. Here as well light is coming. Here as well light is coming. So what I said, the intensity of light may decrease exponentially inside the semiconductor, but if the light is coming from all the side, then what will happen? The carrier profile will be constant only. That means whatever the excess carrier concentration you generated here, the same excess carrier you will be getting here as well. So this is known as uniform illumination. So in the examination they will not write down Nx is constant. What they will write down? There is uniform illumination. So if the word uniform illumination is written, then you will understand that the excess carriers are not changing with respect to the distance. That means in whole semiconductor, in the complete semiconductor, the excess carriers are constant. Not constant, the excess carriers are uniform. Not constant. Constant and uniform both are different words. So excess carrier is having uniform profile. And already you know that NP naught is constant only. NP naught is already constant, right? So what you will understand from here, Et is 0 and Nx is constant. What does that mean? What does this particularly mean? What is the meaning of this whole thing? We have seen it in the first slide. In the very first page we have seen this. Et is 0 and Nx is constant, or you can say Nx is constant. Wrong word. Nx is uniform. Really sorry. Nx is uniform. Constant is the wrong word here. Nx is uniform, that means it is not changing with respect to the distance. So what do you think, what will be the answer of this particular thing? That means your djx by dx would be equal to 0. Why is that so? Because E is 0, that means drift current is 0. If Nx is constant, what does that mean? The diffusion current is 0. So total current would be 0. Then differentiation will surely be 0. So what did you see here? This term is gone. This term is also gone. This term is gone. This term is also gone. Basically 0 would be equals to 0 plus generation rate minus recombination rate. So from here what you will get to know is that generation rate would be equals to the recombination rate. So at a lot of places you would see that under steady state generation rate is equals to recombination rate. Is that statement true? That under steady state generation rate is equals to recombination rate? Absolutely wrong. Under steady state, for the case of uniform illumination such that there is no electric field is applied, then your generation rate is equals to recombination rate. So never ever tell that, sir, under steady state generation rate will be equals to recombination rate. I will show you a question of GATE 2022 examination. There steady state will be mentioned, but generation rate will not be equals to recombination rate, because these conditions will not be satisfied there. They will give this condition, they will also give this condition as well, but they will not talk about this particular condition. So there you cannot say that, sir, generation rate will be equals to recombination rate. Is that okay for you or not? So generation rate will be equals to recombination rate when your djx by dx is 0. And when djx by dx will be 0, if electric field is 0 and Nx is uniform. That means there is a case of uniform illumination. That means at all the, as you move into the semiconductor, at all the values of x, there is same carrier concentration. Okay. Now again, under steady state you already know that dNt by dt would be 0. Et is 0. What does that mean? Drift current is 0. And Nx is linearly varying. What I am saying? Nx is linearly varying. If Nx is linearly varying, what does that mean? If Nx is having linear variation, that means your drift current is constant, and if you do the, your drift current is not constant. Your drift current would be uniform. I should not say constant. Even in the first slide as well, I have written constant. Okay, here I should have written uniform. Uniform. Uniform means it should not be changing with respect to the distance. Uniform, not constant. Uniform. Okay, uniform, uniform. Here also uniform. this is also uniform. So now which case we are discussing? This case we are discussing, right? So if your nx is, yeah, here you can write down constant, right? Here you can write down a constant value. Why I can write down the constant? Because it will be a particular value, no? So uniform, constant, both will have the same meaning. So here the slope will be constant. Slope will give a particular value. And if you do the differentiation of a diffusion current, then what you will get? 0 only. So whatever the two conditions that we discussed in first two pages, those only our special case are. So these are our special case. So here as well you would know that this will be equals to 0. What does that mean? That means here also generation rate will be equals to recombination rate. So generation rate will be equals to recombination rate if you are under the steady state, applied electric field is 0 and your profile is either uniform or linearly varying. What I am saying, generation rate is equals to recombination rate under steady state, applied electric field is 0 and your profile is either uniform or linearly varying. Is that okay for you? Okay. There was one more condition, by the way. The total electric field was constant and your profile was uniform. In this condition as well, what was happening? In this condition as well, dgx by dx was 0, right? Because if this profile is uniform, that means your diffusion current is 0. And if your total electric field is constant, then your if total electric field is constant, then oh, this is an error we have done, I guess. No, sorry. Here n is also constant, no? N is uniform, nx is uniform. So this is uniform. That means nothing is depending on x. Electric field is not depending on x, mu is not depending on x, q is not depending on x, and n is also not depending on x, right? This is also uniform only. So everything is uniform. Then you do the differentiation with respect to x, what you will get? 0 only. So this was also a condition, but it is not very famous. What you would see in the examination is that they will give electric field, external electric field 0 only. Basically, in the examination, till this date, whatever the question have been asked, always this condition and this condition was given, always. So that's why people usually don't discuss that it is equals to constant. Like if total electric field is constant and your profile is uniform, that means if there is a case of uniform illumination with the constant electric field, then also your dgx by dx would be equals to 0. Along with that, under steady state as well. So under steady state, if steady state is there, what does that mean? Under steady state, and if steady state is there, that means dn by dt is equals to 0. So this is 0, dgx by dx is 0. What does that mean? Generation rate is equals to recombination rate. Okay. So three conditions are there, but you remember only one thing: steady state you need to see, okay, and then profile you need to see. ET 0 will be given. Steady state, ET 0, profile. Profile is uniform or linear. Then your generation rate will be equals to recombination rate. Don't feel like that, sir, there is too much. There is nothing too much, right? Very, very simple thing. Now a very easy question, try solving it. The correct form of a continuity equation for a semiconductor under non-equilibrium is, sir, this formula you have told, this formula also you have told. Sir, from where these formula came into action? Try doing it on your own. You should be able to do it. These formulas are also there, no? Just write down the expression of j and x. What will be the expression of j and x? That could be n, q, mu. This could also be a function of x. Electric field, okay, plus q dn dnx by dx. And when you do the differentiation, what you will be getting? Differentiation divided by q. So q and q will get cancelled out. Now what you will see here, this is also a function of x, this is also a function of x. So u into v formula I will apply. What does that say? One as it is, first one as it is. So first one as it is, differentiation of the second, plus second one as it is. That means mu into, why sir, why you are not applying q? Because q is gone, no? Because I have divided by q. So this q I have taken this side. Now what I am doing? I am doing the differentiation. So differentiation of, first I am doing the differentiation of nx ex as it is. Then I will do the differentiation of ex keeping nx as it is. Here also I need to do the differentiation again, so that will be double differentiation. Okay, so 1 by q here gnx by dx. So what you can see, mu ex, yeah, so mu e, this term is here, right, this term is here, this term is here, and generation rate minus recombination rate is already given, right. Similarly, all these terms are coming in, all these terms are coming for holes as well, just there will be a extra negative sign. Where there will be extra negative sign? Why there will be extra negative sign? Because you know that whenever we write down for the holes, extra negative sign we add up. So here negative sign is there, here negative sign is there, and why there is no negative sign here? There should be negative sign here as well, no? Right. There is some error. If I put here negative sign, I will put basically negative sign I will put, so negative. Yeah, negative sign will not come here. It will be positive only. Why is that so? Because for holes, what you will write down? This will be your JPX, no? This will be your JPX. What will be your JPX? N Q mu E. And when I write down the diffusion current, for holes, then again negative sign will come, no? So Q into dP dpx by dx. So here in place of N, I need to put P. Now this Q I will take this side, and then I will differentiate. Mu Ex as it is, then dpx by dx, plus then mu px as it is, dex by dx, minus dp d square px by dx. Okay, but extra negative sign I need to add. So this will be negative, this will be negative, and this will be positive. Now you can check what you can see: negative, negative, positive, generation rate minus recombination. So all options are correct. Okay, so only in the options this kind of question can be asked. These formula you don't need to remember. That's why I will remember this answer. Practically impossible to remember, no? Actually, people will find this one to remember as well. Like this also will be difficult to remember. But we have developed the intuition that total increased concentration with respect to time would be equals to generation rate minus recombination rate. Now, carrier concentration because of the current will also increase. So what term will come? 1 by q dgx by dx. So this will be easy to remember without any mathematics, right? After that, if it is required, you can derive it, but in the examination, this will never be used. These will never be used in the examination. Only in MCQ they can ask, or MSQ they can ask that what is the correct form of continuity equation for semiconductor under non-equilibrium. So this is how you can tell the answer. All good? All fine? So now our task would be just to solve the problems. So for 2 hours, we have understood the complete theory. Now we will be just doing the problem solutions. So questions will be there and we need to solve it. That's it. So how we would approach the problems? Although you don't need to mug it up, but what you will be first looking at it? You will be looking at the special cases. That means you will be looking for which condition? Steady state. First thing is steady state, electric field 0. I am writing down. Steady state, electric field 0, and carrier profile is either completely uniform or linearly varying. If this thing is there, then you will directly do generation rate is equals to recombination rate. And what is the formula of recombination rate? That is equals to delta p divided by tau p, delta px divided by tau p, and since we are looking at a steady state, so let's write down in a better manner. Since we are looking at the steady state, so now nothing will be a function of time t. All the things will be function of x only. So all the things will be function of x only. Why is that so? Because we are at the steady state. So at the steady state, recombination rate and generation rate both will be equal and both will be function of x. And what is the formula of recombination rate? That is equals to delta px divided by tau p, or delta nx divided by tau n. So this I will apply in n type, and this I will apply in p type. Okay, so this will be our best case. And secondly, constant and uniform lifetime. Constant and uniform lifetime. This is also very important. Why it is very important? Because whatever the formula that you have written down, this formula is applicable only for this case, that your lifetime should be uniform. It will be surely constant, there is no doubt about that, but it should be uniform as well. It should not be a function of x. Okay, as you go into the semiconductor, as you move into the semiconductor, your lifetime should not be changing. If it is changing, or if it is not mentioned, that they did not even discuss about lifetime, then you cannot take it uniform, then you cannot apply this formula. Is that okay for you? And if worst case otherwise, then you have to go for continuity equation. And there is only one question till this date in the gate history that you need to go to continuity equation. Although luckily in that question, even if you solve it without continuity equation, you are getting the correct answer. But that was lucky. So I will solve that question without continuity equation, and then we will see that we are getting the correct answer. Then we will see what wrong thing we are doing and how to make it correct. What will be the correct answer of that particular thing. So great discussion we are going to do on that particular question. But as of now, the summary is clear to you. This is the only summary for solving the problems. That's it. Questions will be solved from here. Whatever that we have studied, that we have built up the base. But from the continuity equation, this is how the questions will be solved. So let's get started. Everything that we have studied, that will be surely helpful. Okay. So let's get started. This is the first question. All these questions are from our Niemann's book. Okay, Donald Niemann book, Semiconductor Physics by Donald A. Niemann. So from there only these questions are picked, and most of the gate questions are framed from that particular book only. Like 90% of the gate questions are coming from that particular book directly, just by changing some data. So let's get started. Although this is written by ChatGPT, because what I do is that I give them prompt, like I change some of the values of the questions and then I put it here. So that's why just I try to make it more exam oriented. Right, whenever like any writer is writing down the book, then he is not writing down for any examination purpose. He is writing down that PhD guys might be studying it, MTech guy might be studying it, even BTech guys might be studying it. So everyone should be able to understand what they are doing. It doesn't mean that he is writing down the textbook to make you pass for a competitive examination, right? NPTEL lectures and these textbooks are never made for competitive examination. They are made for the understanding purpose. So that's why as an educator, it is our duty that we read it, we make a good conclusion out of it, and then represent in front of you so that it would be helpful for cracking the competitive examination. So yeah, let's get started with this question. N-type gallium arsenide semiconductor is there. N-type it is, and this was the donor concentration. It is illuminated at T equals to 0, generating 10 to the power 14 electron hole pairs per centimeter cube. What does that mean? This is your generation rate. So N-type semiconductor was there. It was at equilibrium. Donor concentration was 10 to the power 16. Okay. And Ni value is also given. Ni value is also given. So you can see that donor concentration is much higher than Ni. So what does that mean? Approximate number of holes will be equals to 10 to the power 16 only. Right. And so the approximate number of electrons will be equals to 10 to the power 16 only. And what will be the number of holes? That will be Ni square by Nd, Ni square by N. 10 to the power 20 divided by 10 to the power 16, that would be 10 to the power 4 centimeter cube inverse. So this was the equilibrium. Then what really happened? At T equals to 0, they illuminated the light and generating 10 to the power 14 electron hole pair per centimeter cube at steady state only, like this is the steady state concentration they would have given. That means at steady state 10 to the power 14 extra electron hole pairs are generated. What does that mean? That means the value of delta Px is equals to delta Nx is 10 to the power 14 centimeter cube inverse. Did you understand this point or not? Do you agree to this point? Say yes or no. Surely you agree to this point, no? Right? Because these many electron hole pairs are generated. The illumination is turned off at 50 nanosecond. Given that the minority whole lifetime is 10 nanoseconds. So whole lifetime is given, that is 10 nanosecond. Determine the whole concentration at 15 nanosecond and 60 nanosecond. So very simple question. What was the scenario? What was the scenario? The scenario was like this. initially you are having, we will be talking about the minority carrier concentration, right? So initially you are having 10 to the power 4 here. Then at t equals to 0, they turned on the light. At t equals to 0, they turned on the light. They turned on the light at t equals to 0. So now what will happen? The concentration will try to increase. The concentration will try to increase. Basically, the number of holes will try to increase. Already they are having 10 to the power 4. So they want to reach to 10 to the power 14 plus 10 to the power 4. Basically, they need to generate more 10 to the power 14. So what will be the equation? The equation will be, if I write down delta P T, that means they want to reach to 10 to the power 14 starting from 0, e to the power minus t by tau P minus 1. Oh, sorry, 1 minus e to the power minus t by tau P. Capacitor equation. Capacitor wants to charge to 5 volt starting from 0. Now no one will say that, sir, we are starting from 10 to the power 4. 10 to the power 4 is the constant thing that it will always have. Right? Are you able to understand this point? 10 to the power 4 it will always have. There is no one who can change it. We are just focusing on the excess carrier that are generated. So 10 to the power 14 are the excess carrier that are generated. Right? So this equation we have already discussed in great detail. Now you are able to understand what is happening. Now what they are asking at 15 nanosecond. At 15 nanosecond, what will be the concentration? At 15 nanosecond. And tau P value is also given, that is 10 nanosecond. So you can write down. It wanted to reach to 10 to the power 14. But in 15 nanosecond, how much it would have reached? In 15 nanosecond, it would have reached. I have spent more than enough time. I have made the diagrams as well. So I hope you would be able to understand. Otherwise, it would become very difficult that what is happening, you wouldn't even know. Right? Instantaneously, they cannot generate 10 to the power 14. They will take some time. So they want to reach to 10 to the power 14 at the steady state. So this is how I will write down the equation. The switch is turned on at t equals to 0 nanosecond and at 15 nanosecond it is turned off. So what will happen at 15 nanosecond, we will see that. But first our target is to find out at 15 nanosecond. So 15 divided by 10. So what will be the answer? A to the power 1.5. A to the power so 0.77 into 10 to the power 14 centimeter cube inverse. So your excess carrier concentration at 15 nanosecond is this much. So this is the excess carrier concentration. So what will be the total? So total hole concentration at t equals to 15 nanosecond. That would be equals to what? These are the excess plus something that I already have. So I already have 10 to the power 4 plus excess, which is 0.77 into 10 to the power 14. So what you will get? 10 to the power 4 is approximately nothing in front of 10 to the power 14. 0.77 into 10 to the power 14 centimeter cube inverse. So this is the answer of the first one. Very simple, very straightforward. Now what is happening at 50 nanosecond, at 50 nanosecond, you are turning off the switch. So what will be the concentration at 50 nanosecond? First I need to find out that thing, because I know that since light is gone at 50 nanosecond, the light is gone. So now after that what will happen is that it will decrease. But I am not pretty sure that at 50 nanosecond have we reached to this value or not. Are you able to understand what I am saying? At 50 nanosecond, it might happen that you wanted to reach to 10 to the power 14, but it might happen that you were not able to reach here at 50 nanosecond. Like what I mean to say is that what if he turned off the switch at 15 nanosecond only? At this time only he turned off the switch. Then what would have happened? Then your excess carrier concentration would be decreasing from this value, not from this value. So first I need to see at 50 nanosecond what is the scenario. Although I directly know that my time constant or carrier lifetime is 10 nanosecond and this is 50 nanosecond. So at 5 tau P time approximately I will reach here. If you know network analysis in a good manner, then in thrice of the time constant, this is like a time constant only, no? So in thrice of the time constant, you reach to the 95% of the value, and in 5 times of the time constant, you reach to the 99% of the value. So forget about all these things, just apply the formula. What I am saying is that first we need to find out that what is our concentration at 50 nanosecond. Have we reached to our steady state or not? So excess carrier concentration I am finding at 50 nanosecond. Divided by 10, right? Divided by 10. So e to the power minus 5 will be a very, very low value. Minus 1. So you can see that 99.3. So answer is coming 0.9932 into 10 to the power 14 centimeter cube inverse. So this much you have reached. So this is the concentration at 50 nanosecond. Okay. Now the switch is turned off. Switch is turned off at 50 nanosecond only. Switch is turned off at 50 nanosecond. Now what will happen to the excess carrier concentration? The excess carrier concentration will decrease from this particular value. What is this value? 0.9932 into 10 to the power 14. From this particular value, it will exponentially decrease. Starting from 15 nanosecond, right? Divided by tau p. What is tau p here? Tau p is 10 nanosecond. Is that clear to you or not? Let's put tau p only. So after that, it will decrease. Basically, in 10 seconds of the window, when you turned off the switch, in 10 seconds of the window, you are checking at 60 nanosecond. What does that mean? After turning off the switch, after that, after 10 nanosecond, what is your condition? When you turned off the switch, after that, after 10 nanosecond, what is the condition? Or they have simply written at 60 nanosecond, what is the condition? Did you understand this point? That's why we put t minus 50. Do you understand? Because here I'm going to put 60 here. So window of 10 nanosecond was there. So what I'm going to do is that here I'm going to put 60 nanosecond. So 60 minus 50, that means window of 10 nanosecond. So what I will be getting? 0.9932 into 10 to the power 14 e to the power minus 60 minus 50, that would be 10 nano divided by tau p. So 0.9932 divided by E. So 0.36 into 10 to the power 14 centimeter cube inverse. This is the excess concentration at 60 nanosecond. So what will be the total concentration? Total whole concentration at 60 nanosecond. So this is the excess one. Plus we know that this will always be there. 10 to the power 4 will always be there. So what you are getting? Approximately 0.36 into 10 to the power 14 centimeter cube inverse. So although in the examination this question will not take that much of time, what I will think directly, I will see, okay, at 10 t equals to 0, illumination has started. That means excess carrier will start generating, but it will not generate instantaneously. It will take some time. Exponentially it will rise. Exponentially it will rise. It needs to reach to 10 to the power 14. So equation would be 10 to the power 14 1 minus e to the power minus t by tau. So at 15 nanosecond I can find out the answer. Now what I can see that at 15 nanosecond, at 50 nanosecond, the switch is turned off. That means the illumination is turned off. So what will happen is that whatever the excess carrier has been generated, they will exponentially decay to our equilibrium concentration, right? So then I would see that 50 nanosecond, that means my time constant is 10 nanoseconds. So 10 to 50, 5 tau time is there. That means surely I have completely reached to the excess carrier concentration. Steady state excess carrier concentration I have already reached. So 50 nanosecond is actually the steady state only. So this much concentration I am already having. Now what will happen is that it will decrease exponentially. So from 10 to the power 14, nearly about 10 to the power 14, it will exponentially decrease. So from 10 to the power 14, it is exponentially decreasing. So e to the power minus t by 2. T minus 50 nanosecond I can write down, but I would see that from 50 to 60 nanosecond they are asking. That means I am having a window of 10 nanosecond. So here 10 nanosecond will come. So 10 nano divided by 10 nano. So answer would be this one. Very easily you would be able to solve, right? Let's go to the next one. N-type semiconductor with donor concentration is this much, illuminated uniformly. What does that mean? That means since this is N-type semiconductor, so I would be focusing on minority carrier concentration. So this is uniform. right? This much is calculate the answer under steady state. You read the question and you see under steady state. Did they discuss about electric field anywhere? That means electric field is also 0. They did not discuss about electric field anywhere, no? So total electric field is also 0. What does that mean? That means generation rate is equals to recombination rate. Generation rate is equals to recombination rate, and that is given as 10 to the power 20 centimeter cube second inverse. Can I apply the formula? You can apply the formula if your lifetime is constant. Lifetime is constant. So the recombination rate is given as 10 to the power 20. Can I apply the formula? Yes. What they are asking? Excess majority carrier concentration they are asking. But you know that, sir, here I will put the formula of minority carrier concentration. Why is that so? Why minority carrier concentration? Sir, because, sir, if I put the minority carrier concentration here, then I will be able to use this lifetime, because my minority carrier concentration is holes. So excess minority carrier concentration I am putting here divided by the lifetime. So excess minority carrier, since it is uniformly illuminated, so there is no meaning of writing down X here. I will directly write down delta P. Why I am directly writing delta P? Because uniform illumination is there, no? So whatever the excess carrier that has been generated, let us say any value that I get, that will be uniformly distributed. That means that will not change with respect to X. And since you are already at steady state, so it will not change with respect to time as well. So there is no variation with respect to space and with respect to time. That's why you can see that generation rate and recombination rate are constant and uniform. They are neither depending on the X, nor they are depending on T. Everything is crystal clear to you. Every single thing that is written in this question, that is clear to you, and this is the way of solving any problem. That whatever that is written in the statement, everything should be clear, right? So delta P by tau P value is 10 microseconds. So from here you can see your answer would be coming, delta P would be 10 microseconds. So 10 to the power 20 centimeter cube divided by second into 10 microsecond. 10 microsecond. Okay, second to second will get cancelled out. 10 to the power 15 centimeter cube inverse. This is your delta P. But what they are asking? They are asking the value of delta N, excess majority carrier concentration. And who are the majority? N. That means they are talking about excess majority carrier concentration, which will be excess holes. How many excess holes are generated? You know that electron and hole pairs, electron and holes are generated because of the light illumination. Electron and holes will be generated in pairs. So that would be only equals to delta. Everything is crystal clear, very simple question. Okay, generation rate was given, that would be equals to recombination rate, but condition you need to see, because usually I have seen that people will just remember generation rate equals to recombination rate, forget about the continuity equation. They don't even care about the continuity equation. Generation rate equals to recombination rate, this is the formula. But there are a lot of things. How generation rate became equals to recombination rate? When you can apply this formula. So this was also very, very important, that it is not a function of space, it is not a function of time, then only I can apply this formula. Okay, so a lot of things are there, then only you can apply generation rate equals to recombination rate. So before 2022, in all the question, this thing was working. In GATE examination, in all the problems, this thing was working. But in 2022, there was one question that changed everything. Okay, so you need to take care of all these things, right? Consider one-dimensional hole flux as shown in figure. Figure they have not given. If the generation rate of holes in the differential volume, generation rate they have given 10 to the power 20 centimeter cube second inverse. Recombination rate they have given. So here generation rate and recombination rate are not same. What must be the gradient of in the particle carrier density to maintain the steady state hole concentration? Steady state. Now, what do you mean by gradient? Gradient means variation with respect to space. What I am saying? Gradient means variation with respect to space. But in EDC, we only take the variation with respect to x-axis only. Or y axis or z axis. Basically we focus on 1D variation, but when we go to EMFT we focus on 3D variation. So that's why we use the sign of gradient there. But here what we will use, dy dx. So what they are asking, they are actually asking dp by dx, sorry, what I am doing, djp by dx. This is what they are asking. Will it be depending on x? No. Why is that so? Because generation rate and recombination rate are not depending on x. Although we will consider that it is depending on x, but when the final answer would come, we will know that it is not depending on x. Oh, sorry. Like this whole value will not depend on x, but the generation, this carrier density is depending on x. What I am saying is that this carrier density is surely depending on x. This whole answer is not depending on x. Because if carrier density is not depending on x, let's just say this carrier density is a constant value, then what will be the value of this one? 0, no? So carrier density is not a constant value here. Are you able to understand this point? Okay. So this is what we need to find. What we need to find? What we will do is that we will apply our continuity equation. So what will our continuity equation will say? 0 would be equals to minus 1 by q d jpx by dx. What is written? Gradient in the particle current density. Gradient in the particle current density. This is the meaning of a gradient. D by dx, current density. So this is what I need to find. Gradient in the particle current density plus generation rate minus recombination rate. Usually we write down generation rate minus recombination rate. Right? So from here what do you see? Usually we write down as capital G. So here what do we see? Q into generation rate minus recombination rate. What is the value of Q? 1.6 into 10 to the power minus 19. Where is Q? Q is not given. Generation rate minus recombination rate. 10 to the power 20 minus 2 into 10 to the power 19. 10 to the power 20 minus 2 into 10 to the power 19. So 10 into 10 to the power 19 minus 2 into 10 to the power 19. So what you will see? 10 minus 2 will be 8. So 8 into 10 to the power 19 you will be getting. I hope you know how to do this calculation. Right? 10 minus 2, 8 into 10 to the power 19. So this and this is getting cancelled out. 1.6 into 8. 1.6 into 8. So 12.8. Now what will be the unit? Centimeter to the power minus 4. Why is that so? Because current, sorry. What is the unit of current density? That is ampere per centimeter square divided by another centimeter. So unit will be ampere into centimeter cube inverse. Gradient in the particle current density. So current density is ampere per centimeter square divided by another centimeter. So answer would be ampere into centimeter cube inverse. Ampere into centimeter cube inverse. This will be the answer. Very simple. And why centimeter? Because sir, everything is going into centimeter. Right? All good. And you can see here is that this is centimeter cube, and this is per second, and charge unit is coulomb. So from there ampere would come and centimeter cube will remain there as it is. Okay. So very easily you can write down the unit as well. Answer would be 12.8. Although the answer of this particular question, I saw the answer in some on internet somewhere, but that was given wrong. Okay. They forgot to multiply with 1.6. So if you find the answer on internet and anywhere, they gave the answer like this, but that is wrong. Okay. You need to multiply with 1.6 as well. So don't forget this Q as well. Okay. This question also asked in gate examination only. Consider a long rectangular bar of a direct band gap p-type semiconductor. The equilibrium hole density is 10 to the power 17 and intrinsic carrier concentration is 10 to the power 10. So what does that mean? Holes are 10 to the power 17 cube inverse and equilibrium carrier concentration is, intrinsic carrier concentration is 10 to the power 10 centimeter cube inverse. What does that mean? The number of electrons would be 10 to the power 3 centimeter cube inverse. Okay. Electron and hole diffusion length are given. That means diffusion length of electrons electron and diffusion length are given. So diffusion length of hole is 1 micrometer and diffusion length of electron is 2 micrometer. Okay, this is given. The left side of the bar at x equals to 0 is uniformly illuminated with laser having photon energy greater than the band gap. That means this energy is greater than the band gap. This is what they are saying. And if this energy is greater than the band gap, what does that mean? Electron hole pair will be generated. Okay, excess electron hole pairs are generated only at x equals to 0 because of the laser. The steady state electron density at x equals to 0 is 10 to the power 14. So at steady state, that means it will vary with the time, but at the steady state you have reached to 10 to the power 14. So excess electron hole pairs, that means delta P is equals to delta N, that is equals to 10 to the power 14. Okay, at x equals to 0, at x equals to 0. Okay, due to laser illumination. Under these conditions and ignoring electric field, the closest approximation of the steady state electron density at x equals to 2 micrometer is. That means they are asking with respect to the distance. They are asking with respect to the distance. So how it will be decreasing, that you need to tell. So I told you by default we need to take exponential decrease. So whatever the length could be there, I don't know what is the length of the semiconductor, but what they are asking at 2 micrometer. So at 2 micrometer, what will be the excess carrier concentration? They are talking about only excess carrier concentration. No? The closest approximation steady state electron density they are asking. They are asking about the complete electron density at x equals to 2 micrometer. So these many electrons I already have, 10 to the power 3, and excess electrons are also generated. Excess electrons are also generated, which will be a function of x. Why is that so? Because there is no uniform illumination. They are saying that I am doing the illumination only at x equals to 0. So first I am doing the illumination at x equals to 0, and at steady state 10 to the power 14 has reached. But if you go into the semiconductor, as we move into the semiconductor, the intensity will decrease exponentially. So exponentially these electron concentration will decrease, right? So e to the power minus x by Lp, where Lp is the diffusion length. Okay, so this formula specifically I cannot write down because it may happen that it may decrease exponential, or it may happen linear, or it may happen it could be constant as well, right? But by default here nothing is mentioned, we have to take exponential. And from the options as well you can see that it would be exponential only, 0.37, 0.63. So this is the value of 1 by E. So you can use your brain, right? And here why I am writing down Lp, this would be Ln, right? Did you understand how did I write down the formula? Because I know that exponential decrease would be there, no? So 10 to the power 14 e to the power minus x by, now here what I should write down? I should write down something related to length only, that is the diffusion length, 2 micrometer. So from now onwards you can remember the formula if you are not able to understand. 10 to the power 14, that is the concentration at x equals to 0 with respect to the distance, it will reduce exponentially. So 10 to the power 14 e to the power minus x by Ln. Okay, because this will be micrometer and this will also be micrometer. So in the e to the power you will get some constant value. This is our target. So length micrometer and this is also micrometer. Now it is not just related to this particular subject. In the whole electronics question paper, electrical question paper, in instrumentation question paper, whenever you don't know what kind of profile you will get, what I am saying, in any of the question paper, whether it is about EM wave or whatever it is, when you don't know what kind of profile you will get, by default take it exponential. Let's say some wave is coming having an amplitude of P naught. They are asking the amplitude of the wave at 2 micrometer. What you will do? Sir, P naught e to the power minus at 2 micrometer they are asking. Now in the question I will find something having a unit of meter inverse. Okay, so if I get something having a unit of meter inverse, then I will simply multiply. And if I get something having a unit of a meter, then what I will do? I will divide. Because in e to the power something constant I need to have, no? Like I cannot find the value of e to the power 2 centimeter square. Doesn't make any sense. I can find the value of e to the power 2. I cannot find the value of e to the power 2 centimeter square. So this is known as like absorption coefficient. In most of the examination, what will be written? Absorption coefficient. Absorption coefficient, that will be alpha, and that will have a unit of meter inverse. Here we are using diffusion length. So 1 by ln I am writing. If you see closely, e to the power minus x multiply with 1 by ln. So e to the power x, x will have a unit of micrometer, 2 micrometer. I need to find that 2 micrometer. What will be the unit of 1 by ln? That would be micrometer inverse. So micrometer will be cancelled out with micrometer inverse, right? Very simple thing. So this I am telling for every single thing. I remember during my instrumentation question paper, there was question from optoelectronics. So I never studied optoelectronics, right, in instrumentation, because it is not in our GATE syllabus. But two questions of optoelectronics I was able to solve just by using my intuition. One I solved using aptitude only. That question was based on Doppler effect. So Doppler effect you can understand by simple aptitude. So that I solved using simple amplitude, and one was like what will be the intensity at a particular distance. So there also I know that blindly I should go with exponential. So there also I applied the same thing, exponential, and it went correct. But in EM wave, in power something different happens. I hope you remember. In optical fiber as well, when it comes to power, the different formula come into action. So you can revise your EMFT notes. There I told you to specially focus on optical fiber. In optical fiber, the formula of power is different, right? So there you can revise your notes, you will be able to see that. Yeah. So 10 to the power 14 e to the power minus x by ln. So at what point I need to find? At 2 micrometer I need to find. So electron concentration, excess electron concentration at 2 micrometer, that would be 10 to the power 14 e to the power minus 2 micrometer divided by ln. What is the value of ln? 2 micrometer. So that would be 10 to the power 14 e to the power 2 will get cancelled out, micrometer will get cancelled out, 10 to the power 14 e to the power minus 1, and 10 to the power 14, this 10 to the power 14 was having a unit of centimeter cube inverse. So what will be the answer of delta n you are getting at 2 micrometer? That is 1 by e. 1 by e is 0.37, right? Let's check it again just for our confirmation. Yeah, 0.37. And equilibrium electron concentration is equilibrium electron concentration in p-type semiconductor. In p-type semiconductor, equilibrium electron concentration is 10 to the power 3 centimeter cube inverse. So total electron concentration at 2 micrometer, that would be given as 0.37 into 10 to the power 14 plus 10 to the power 3. So approximately it will be equals to 0.37 into 10 to the power 14 centimeter cube inverse. So this will be the answer. Very simple question, very straightforward. You should be able to solve it. The only thing was this thing, that if the profile is not given, I will take it exponential. So from 10 to the power 14, it will reduce exponentially. Let's go to the next one. A semiconductor has a cross section area of 1 centimeter square, thickness of 0.1 centimeter. That means you can find out the volume. Something will be happening with respect to the volume as well. Determine the number of electron hole pairs that are generated per unit volume per unit time by uniform absorption of 1 watt of light at a wavelength of 6300 angstrom. A very good question. Assume each photon creates 1 electron hole pair. So from 1 photon you get 1 electron hole pair. Second, if excess minority carrier lifetime is 10 microsecond, then what is the steady state excess carrier concentration? All good? All fine? So let's get started. So this was your semiconductor having thickness whatever it is. Let's talk about the dimension later on. But what is happening? Electron hole pair are generated because of the light that we are putting, right? Because of the light. So light is having a power of 1 watt, and it is having an energy of hc by lambda, right? It is having an energy of hc by lambda. So what will be its energy? So value of h 6.63 I am putting. Like if I put I can put this value as well, because I remember this value. I told you I will remember this value. 1242 electron volt nanometer. 1242 electron volt nanometer divided by lambda. Lambda is 6300 angstrom. Angstrom means 10 to the power minus 10 meter. But I need to convert it into the nanometer. So 10 to the power minus 1 I will take here. So 630 nanometer. So here I will put 630 nanometer. Now what I will be getting? 1242 divided by 630. 1242 divided by 630. So nanometer to nanometer is getting cancelled and I am getting 1.97 electron volt. This is the energy. But what is this power? 1 watt. What is watt? Do you remember this formula? E is equals to PT and power is equals to energy per time. That means in 1 second you are having 1 joule of energy. What they are saying, in 1 second you are having 1 joule of energy. If power is 2 watt, that means in 1 second you are having 2 joule of energy. Per second, how much energy? So the wave that is coming or the light that is coming, that is having in per second it is giving you energy of 1 joule. What I am saying is that light energy per second, that is 1 joule. This is the total energy of light per second. Now what is the energy that we have found out? 1.97 electron volt. So we need to convert it into the joule, because calculation we are going to do in the joule. What you can do, either you convert this into electron volt or you convert this electron volt into joule. So we will convert this electron volt into the joule. Okay. So 1 electron volt is equals to how much joule? Did I tell you to remember? No. I told you simple, go by the formula Q into V. So if 1.6 into 10 to the power minus 19 coulomb gets a voltage of 1 volt, then it is equals to 1 electron volt. And coulomb into volt is equals to joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19. 1 electron volt is equals to 1.6 into 10 to the power minus 19. So you don't need to mug it up. Okay. Just go by the simple formula. So 1.6 into 10 to the power minus 19 joule. So into 1.6. So 3.15. 3.15 joule. Now what is this? 3.15 into 10 to the power minus 19 joule. This is the energy of 1 photon. This is the energy of 1 photon. Are you able to understand what I am saying? If they are saying that this is the energy of light, that means this is the energy of a light is having a wavelength of this much. That means it will have this much of energy. So this energy will be of photon. So in EDC, whenever you write down the answer of energy, you will always write down per photon. So 1 photon is having this much of energy. Now you are having how much energy? 1 joule energy you are having. What I mean to say is that this was my power. This power was giving me, sorry, this was my light. This light was giving me 1 joule of energy per second. In 1 second it was giving me 1 joule of energy because power was 1 watt. It was having a wavelength of this much. What does that mean? That means per photon in this light there will be a lot of photon. In this light there will be this is the whole light. In this whole light there will be a lot of photon. And the complete light is giving me 1 joule of energy per second. And I know the energy of 1 photon. This is the energy of 1 photon. What I mean to say is that this E is equals to hc by lambda. This is what? This is not the energy of light. This is the energy of photon. Energy of photon. Energy of photon. So this is not the energy of light. This is the energy of photon. Energy of light per second is 1 joule actually. This is energy of 1 photon. What does that mean? That 1 photon is having energy of this much. 1 photon is equals to this much energy. That means in 1 joule, how many photons you will have? That means this much energy is equals to 1 photon. That means 1 joule will be equals to what? 1 joule will be equals to what? So this will go downward. 3.15 into 10 to the power minus 19 photon. Because you know that your light is giving you 1 joule of energy per second. Why I am focusing on 1 joule? Because the light was having a power of 1 watt. That means in 1 second it is giving you 1 joule of energy. Now energy of 1 photon is coming out to be 3.15 into 10 to the power minus 19 joule per photon. That means 1 photon is having this much of energy. So in 1 joule, how many photons would be there? So 1 by 3.15. That means 31.7 into 10 to the power 17. So in 1 joule, Let's go to the next page. So what does that mean? That means that this is a good question, you just need to understand it. I will again explain it, don't worry. So in 1 joule you are having 31.7 into 10 to the power 17 photon. So what does that mean? That means that your light is throwing this much photon per second. Let's understand it again. Your light was throwing 1 watt power. What does that mean? It was throwing in 1 second, it was throwing 1 joule energy. Till this point everything is clear. Now I know that the wavelength of the photon is 6300. So what will be the energy of one photon? The energy of one photon is 3.15 into 10 to the power minus 19 joule. So one photon is having this much energy. That means this much energy means one photon. But how much total energy you are having? You are having 1 joule of energy. So 1 joule of energy means how much photon? 1 joule of energy means this much of photon. That means your light is having this much of photon per second. That means on this semiconductor, this much of photon are coming per second. Every calculation is going per second. So on the semiconductor, 3.17 into 10 to the power 17 photon per second is being incident. On semiconductor, 3.17 into 10 to the power 17 photon are being incident per second, and each photon will make one electron hole pair, one excess electron hole pair. That means this much photon per second, how much excess electron hole pair they will create. So what they are asking? Determine the number of electron hole pair that are generated per unit volume per unit time. Right? So because of 3.17 into 10 to the power 17 photon per second, 3.17 into 10 to the power 17 electron hole pair will be generated. So in 1 second we are getting 3.17 into 10 to the power 17 electron hole pair. But what we need to find? We need to find electron hole pair generated per unit volume per unit time. Electron hole pair generated per unit volume per unit time. Per unit time means this is your per unit time only, no? Per second this much electron hole pair is being generated. So that would be equals to per second this much electron hole pair is being generated. But per unit volume you need to find. So what is the volume? Here if I find out the volume, so area is 1 centimeter square and thickness is 0.1 centimeter. So 1 centimeter square into 0.1 centimeter. So what is the answer you will be getting? The answer will be 3.17 into 10 to the power 18 centimeter cube inverse second inverse. And this also will have a unit of second inverse only. Why this is having a unit of second inverse? Because per second these many electrons are being generated. Per second these many electron hole pairs are being generated. Is that understandable to you or not? How this final answer came, is that understandable to you or not? This is the final answer. Again let me explain. What they were asking, how many electron hole pairs are generated per second per unit volume. We were having a particular power of a light. That power was 1 watt. That means in 1 second it was giving you 1 joule of power. What was the energy of one photon? Energy of one photon was 3.15 into 10 to the power minus 19 joule. Right? Total energy you were having was 1 joule. And one photon was having this much of energy. That means how much total photon you are having? This much total photons you are having. So on your semiconductor material, these many photons are incident per second. That means each photon will give you one excess electron hole pair. What does that mean? These many photons will give you these many excess electron hole pair per second. So in 1 second, 3.17 into 10 to the power 17 photon per second was generated. This much photons were generated per second. But in the whole semiconductor, in this whole semiconductor, what they are asking? They are asking per unit volume. So I have to divide by volume as well, because they are asking per unit volume. So I have to divide by volume as well. Right? So 3.17 into 10 to the power 18 centimeter cube second inverse. Next, if excess minority carrier lifetime is this much, then steady state excess carrier concentration you need to find. Steady state excess carrier concentration you need to find. Now what is this? Steady state they are talking about, they did not talk about the profile at all, right? So uniform illumination we need to consider, right? Did they talk about the profile? Uniform absorption is there, one light of water. So what I will assume is that I have to make the assumption, because this question is not completely not completely available. So what they are saying is that steady state is there. Okay, steady state is there. What is this actually? This is the generation rate only, no? Are you able to understand this point? This is the generation rate. These many electron hole pairs are being generated per unit volume per unit time. That is known as generation rate only. So this what we have find out. We have find out the generation rate. Now steady state is given, right? Steady state is given. Along with that, doping profile is not given. And electric field also they did not mention. So electric field is 0. And now doping profile also I will consider uniform or linearly varying, because they are throwing the light. Now they did not say that I am throwing the light at x equals to 0. So I will assume that they are throwing the light in the whole semiconductor only. Uniform illumination I will assume. Okay. So I will assume this is uniform only. So from here I can say that my generation rate is equals to recombination rate. And that means this will be equals to excess carrier concentration. What they are asking? Excess minority carrier concentration. Minority, majority, what is there? I don't know, because they don't even tell which kind of semiconductor is there. So anything you can assume. So basically I will write down here minority excess carrier concentration, minority excess concentration divided by the lifetime. Okay, so this is your generation rate, multiply with lifetime, that is 10 microsecond lifetime. What that will be? Minority excess carrier concentration. That would be equals to minority excess concentration. So this will be the answer. You can solve it. Okay, this will be the answer of second one. So basically they just, in the first question they were just asking the generation rate, that how many electron hole pairs are generated per unit volume per unit time. So that we have find out by all this calculation. So this question was also very good. This kind of question till this date in the GATE examination has never been asked. So surely it is coming very soon, that they will give the power, they will give the energy of one photon. So energy of one photon you are having, power you are having, per second power you are having. That means you are having joule, you are having the energy per second. From there you will understand that okay, this is actually the energy per second. So from here I can find out the number of photon, and one photon will create one electron hole pair. So these many electron hole pairs are being generated per second. And if they are asking per unit volume, then I will have to divide by the volume. So per unit volume per second I have find out the electron hole pairs generated. That means I have find out the generation rate. That would be equals to recombination rate. If these conditions are satisfied, then I can find out the minority excess carrier concentration if lifetime is mentioned. And lifetime is also constant here. Constant and uniform. Lifetime is constant and uniform. So you will get this particular answer. All good? All fine? Very simple question. Very straightforward. Let's go to the next one. This is also GATE PYQ. This was from Niemann. So those who are having black background, they are from Niemann, and those who are having black background, they are from GATE PYQs. So this is also GATE PYQs. You solve it on your own. You try this question, then you try this one, then try this one, then try this. No, okay, this is just then try this one. So 4 questions you try, and then we will solve this particular question. So 4 questions we will solve in this lecture. Okay, very simple question these are. So you can try all these questions on your own. and then we will solve this particular question, which is the best question of whole EDC till this date. In the examination, they only asked this statement. They did not ask these questions. But if they had asked these questions, then a lot of forget about the students, because I also gave GATE 2022 examination. No one actually solved it. I have talked to GATE 2021, rank 1, rank 3, rank 4. I have talked to all the people. Then did not even read this question. So forget about the students. Students were never able to solve this question. But even the teachers were not able to solve. Now a lot of teachers would say that I was able to solve. But I was a student at that time. No, I know that. Until the answer key came. Answer key came on 21st of Feb. I exactly remember the date. Until the answer key came, there was no one who gave the solution of this question. And whatever the solution that they have given till this date, this is 2025, this is September 2025, I am recording this video. Till this date, they are giving the solution wrong. And I will prove it, that what is wrong in their solution. That's why I added these 4 options as well. I made this question as MSQ. As per them, this will be the answer. But actual answer will be this one. So we will discuss that. This question will be the best thing you would ever see in EDC. Okay. So we will discuss that. Okay. Don't worry. But you try to solve this question. 1, 2, this question as well. Here a little concept will be used. I told you one thing. In the examination, if you don't know about anything, with the distance, always exponential decrease would be there. So if intensity or power here is P naught, then with the distance, it will decrease exponentially. This concept will be used and you will be able to solve this question. So 1 question, 2, 3 and 4. You try solving it. I will take break. I will have my dinner and then I will come back. Okay then. Yeah. Thank you. Yeah. Welcome back, guys. So did you try this question? So let's get started. Silicon is uniformly doped. Length is 0.1 micrometer. Donor concentration is given, that is 10 to the power 16 centimeter cube inverse. This is the donor concentration that is given. Okay, and they did not mention about intrinsic carrier concentration. Then what we need to do is that we need to consider this as a number of electron, right? So number of electron will be 10 to the power 16 centimeter cube inverse, and number of holes at thermal equilibrium. This is the number of electrons at thermal equilibrium. Number of holes at thermal equilibrium, nearly we have to take 0, because they did not mention the intrinsic carrier concentration. So we need to assume that Ni is very lesser than Nd, and then I cannot even apply the mass section law. So Ni value I don't know, Nd value is very large, so I would say that number of holes are approximately 0 at thermal equilibrium. But now what we are doing is that we are illuminating some light, and since we have illuminated the light, electron hole pair are generated at this rate. So how the electron hole pairs are being generated? That are being generated as 10 to the power 17, because GL naught value is given as 10 to the power 17, 1 minus x by L. L value will also be mentioned. No, it is not mentioned. Yeah, L value is 0.1 micrometer, that is mentioned. So this is how electron hole pair are being generated per centimeter cube, per unit volume, per unit time. Diffusion coefficient is given for holes, that is 100 centimeter square per second. Low level injection you need to consider. Linearly decaying steady state excess hole concentration. Linearly decaying steady state excess hole concentration. What does that mean? That means delta Px is linear, right? Whole lifetime is also given. Whole lifetime that is given, that is constant. Whole lifetime is given and it is uniform and constant. So what you understand now? Now I can apply the formula of recombination, right? So this condition is given, right? Steady state is also given. Somewhere it would have been mentioned that they are talking about steady state. Yeah, steady state is also given. Delta Px is also linear. Steady state is also there. What does that mean? That means that your generation rate would be equals to recombination rate, and that would be equals to delta Px by tau p. So whatever that we wanted, everything is given. What all thing we wanted? Tau p should be uniform and constant. Steady state should be there and delta Px should be linear. All these 3 things we want. If these things are there, that means your question is very straightforward. And in 99% of the cases are there that these things would be surely there. Okay. So generation rate is equal to recombination rate. Generation rate is given. What is my target? My target is to find, let's see what we need to find. We need to find the magnitude of a diffusion current density at x equals to L by 2. So I need to find diffusion current density. So diffusion current density could be there because of the electrons as well, because of the holes as well. Because what I know is that in the semiconductor, if I am emitting the light, in the semiconductor, if I am emitting the light, then excess carrier which are generated, let's just say excess holes are generated, then excess electron will also be generated, no, right? So if I make the graph with respect to x, what I am doing, I am making the graph with respect to x. So if I talk about electrons, so at the thermal equilibrium, number of electrons in n-type semiconductor at thermal equilibrium was equals to 10 to the power 16 centimeter cube inverse, and number of holes in n-type semiconductor, at thermal equilibrium was 0, right? Now excess electron will also be generated and excess holes will also be generated. How much they will be generated? Let's find out. So GL is given, not GL, sorry, generation rate is given, that would be equals to recombination rate, and that would be equals to delta Px by tau p, right? So what do you find out from here? This value is equals to 10 to the power 17 1 minus x by L, 10 to the power 17 1 minus x by L. Everything is going in centimeter cube, that we will remember. Tau p value is 10 to the power minus 4. Tau p value is 10 to the power minus 4. So what we will get, delta Px as 10 to the power minus 4, so that would be 10 to the power 13. 10 to the power 13 into 1 minus x by L. This is the expression of delta Px. Now you know that whatever delta Px is there, the same delta Nx would also be there. At x equals to 0, how much you are having? 10 to the power 13. So at x equals to 0, 10 to the power 13 holes are generated, then 10 to the power 13 electron will also be generated. And with respect to the distance, what I mean to say is that here 10 to the power 13 electrons are generated, and here 10 to the power 13 holes are also generated, and with respect to the distance, it is linearly decaying. With respect to the distance, this will also linearly decay, and this will also linearly decay. That means here there is more concentration, here there is more concentration, and here there is lesser concentration. So electrons will diffuse here. That means because of the electrons, this will be the diffusion current, and holes will also diffuse here. Because of the holes, this will be the diffusion current, right? Because of the illumination, the illumination is not uniform, it is linearly decaying. So here the concentration of electrons has increased, here the concentration of electron and holes has increased, while here the concentration of electron and holes are less. Because of that, electron and holes will diffuse and current would come into action. So diffusion current will be there because of the holes as well, and diffusion current will be there because of the electrons as well. So if you want to find out the diffusion current, what all thing you would need? Q you would need, dN you would need, and dNx by dx you would need, right? This is the current because of the electrons, and because of the holes the current is in the negative direction. So here I will put the negative sign. So if I have the delta Px value, then I can differentiate it. I have the delta Px value, I have the delta Nx value as well. So this value I can get. This value also I can get. Q value I already know, and dP value is given. In this question, they did not even give the dN value. So here actually they are asking that diffusion current because of the holes only. What I am saying, they are asking the diffusion current because of the holes, and they forgot to mention it. And this is the same language that came in the GATE examination. I don't remember the year, but this was the same language written. Whenever people solve the question, they will just take the minority carrier concentration and find out the answer. But the doubt may be arising to a student that, sir, the number of electrons that are generated, the same number of the number of holes that are generated, the same number of electrons are also generated. No, so they will also diffuse. That means the current will be flowing in the opposite direction, so the current will be less. Like this is the hole current and this is the electron current. They are flowing in the opposite direction, so current will be subtracted. So ideally, I should take into the action this diffusion current as well. But in the examination, they forgot to mention it, that they are talking about only the minority carrier diffusion current. That means they are talking about the current because of the holes. So there it should have been written the magnitude of the diffusion current because of the holes. So this was the error in this question that I am telling. In the examination, if they had mentioned the value of dn, then the question would become very interesting, because what is our habit? Whenever we solve the problem related to continuity equation or related to semiconductor under known equilibrium, what we do is that blindly we only focus on minority carrier concentration. But just think about it. If the current is coming, then it will come because of the electrons as well and because of the holes as well, and both will be opposite. Both will be in the opposite direction. So one will try to cancel out each other. Basically, they will be subtracted from each other. Are you able to understand what I am saying? Right? So there is an error in this question. They did not mention the value of dn. That's why we will only take that diffusion current because of the holes. If I was there in the examination hall, I would have only calculated the diffusion current because of the holes. Why so? Because I know that there is some error. Because if they wanted to talk about the current because of the electrons as well, they would have given the value of dn. So this is the thing that I wanted to tell. That's why I made this diagram. So what I will write down here, dn value not given. So what I am saying, ignore jn, ignore. So what I will take care into action now, I will only care about jpx, and that would be equals to q dp dy dx delta nx, not delta nx, sorry, not delta nx, here I should have written delta px, q dp by x, dp by dx. What is p? P is equals to, here I should write down px. What is p? Px is equals to number of holes in n-type semiconductor at thermal equilibrium plus number of excess holes with respect to distance x. So this delta px plus at thermal equilibrium, how many holes were there? At thermal equilibrium, how many holes were there? 0 holes were there. And let's just say this value was non-zero. Let's just say this value was non-zero. But will this value contribute in diffusion current? What I am asking, is there any importance of this value for the diffusion current? If I find out dpx by dx, then I know that this value will be constant. This will not be a function of x, because this is there in the whole semiconductor. So this will be always there. Only this will be varying with respect to the distance. So what I will get? At all the places I have seen that directly this formula will be written and question is solved. But there is something wrong in this question that we understood, right? Although finding the answer was not difficult, but there was something wrong that we have understood. Now everything we can do. Although here there will be negative sign as well, but you don't need to care about negative sign. Why so? Because they are only asking about magnitude. They are not talking about the direction. Okay, so when you solve it, what you will get? Q value I already know, 1.6 into 10 to the power minus 19. dp value they have given, that is 100. Everything is going in centimeter. 100. When you differentiate this with respect to x, what you will get? 10 to the power 13 divided by 1 by L. So minus sign is there, minus sign will be there. So 10 to the power 13 divided by L. What is the value of L? 0.1 micrometer. 0.1 micrometer. What is the value of L? 0.1 micrometer. Now just tell me what I should write down here. Think about it, what I should write down. 0.1 micrometer directly I should write down and calculate this final answer. Is that my final answer? Basically I am differentiating it. After differentiating, what I am getting is that 10 to the power 13 divided by L and then negative sign. Value of L is 0.1 micrometers, so that I am putting here 0.1 micrometer. Or let's put L only. So here I am putting the value of L. This negative sign and this negative sign has cancelled out each other, so positive sign is coming. Now in place of this L, what I should put? 0.1 into 10 to the power minus 4 centimeter. Say yes or no, because all the calculation is going in the centimeter, no? Are you able to understand this point or not? So this is a very, very important point. People would mess up here. 0.1 into 10 to the power minus 6 they will write down. But everything is going into centimeter. So whenever the distance is coming, I need to make sure that everything should be in centimeter. So 0.1 into 10 to the power minus 4. So what I am getting? This is 10 to the power 15. 15, this is 10 to the power minus 5. 15, 5, 20. This is 10. So 16. 16 ampere per centimeter square. Because what is the unit of current density, that is ampere per area, and area is going in centimeter, so ampere per centimeter square. There you go, this is the final answer. But this was also a important discussion that we did not consider anything about the electrons. This was the reason. The dn value was not given, so I kind of ignored it. But the same slope that you are getting here, this value would have been same, this value would have been same, but they are saying that dn value, forget about it. Okay, well and good. So they actually mean to ask because of the holes only. Okay, so this question is solved. Let's go to the next one. Yeah, sorry for the interruption guys. So let's solve this question. Silicon is there at 300 Kelvin, uniformly doped with the acceptor atom. Okay, so this is the equilibrium condition, that silicon is there at 300 Kelvin, acceptor atom is uniformly doped, and they are not mentioning intrinsic carrier concentration. That means number of holes will be approximately equals to number of acceptor atom, that are equals to 10 to the power 16 centimeter cube inverse. This is the number of holes in n-type semiconductor at thermal equilibrium, and number of electrons, sorry, this is your p-type semiconductor only, no? And number of electrons in p-type semiconductor at thermal equilibrium will be nearly 0. Why so? Because Ni is not mentioned. This is the scenario, right? Now at t equals to 0, you are throwing the light, and you are throwing the light uniformly. You are throwing the light uniformly. So first thing that we required, that your delta px or delta nx, whatever it is, both will be equal only. Why both will be equal? Because electron and holes will be generated in pairs, and that will be uniform. So first thing I require, that is good, uniform they are. So from here I know that dgx by dx would be equals to 0. Secondly, I can see that carrier lifetime is given, that is 5 into 10 to the power minus 7 second, and generation rate is also given, but they are not saying that it is done at the steady state. So generation rate is equals to recombination rate, nothing can we can do, right? What do you need to find? You need to find conductivity, conductivity as a function of time. So what is your conductivity? What is the general formula that we have studied? General formula n q mu n plus p q mu p. Now this cannot be a function of time, this cannot be a function of time, this cannot be a function of time, and this cannot be a function of time, because these values are already mentioned, mu n mu p already mentioned. Who can be a function of time? This can be a function of time, and this can be a function of time. And why they are the function of time? Because light is being injected. Because of the light, they are the function of time, right? So what will be your sigma t now? Sigma t would be equals to n plus delta nt, because you know that since the light is illuminated at the semiconductor, we will generate electron hole pairs. So whatever the holes are generated, the same number of electrons will be generated. What most of the student would do in this question is that they will forget this one. They will again focus on the minority carrier concentration. They will only take into action delta p. Who is the minority here? Okay, it is p-type semiconductor. So they will only take into action delta n. They will forget about delta p, because it is our habit that whenever we see semiconductor under non-equilibrium, we forget about the majority carrier concentration. So here majority is p. So they will forget about delta p. What people would do, those who have already solved, they would have forgot about this delta p here, I am pretty sure. So this would be your final answer. Now you know that this n is equals to 0. Number of electrons. What is the total number of electrons? Total number of electrons are number of electrons at thermal equilibrium plus the excess electrons, which is a function of time. You know that it will be a function of time. Why it will be a function of time? Because the number of electron or hole pair that we need to generate, they will not be generated instantaneously. They will take some time to reach to its steady state value. So they will be a function of time, and this will also be a function of time. But I know that this is equals to 0, and this value I already know. So now what will be my answer? Delta nt q mu n plus delta pt q mu p plus pp naught, which I already know, q mu p. This is your delta t. Now just let me know one thing. At t equals to 0, what will be the scenario? Will this be there? This would be equals to 0 at t equals to 0. At t equals to 0, delta nt and delta pt would be equals to 0 only. Why so? Because light is illuminated at t equals to 0. So that means there are no excess carriers at t equals to 0. After t equals to 0, the things will start happening. But at t equals to 0, there are no carriers. So if I need to find the conductivity at T equals to 0, at T equals to 0 there are no excess carriers. So delta N at 0 and delta P at 0 would be equals to 0 only. And one thing also I am pretty sure, one thing you know that excess carrier, whichever the excess carriers that are generated as holes, the same number of electron will also be there. So you can say that so delta NT would be equals to delta PT as well, because electron and holes will be generated in pairs only, right? So conductivity at T equals to 0 will be just this PP naught Q mu P, or you can directly say PP naught is equals to Na. So Na into Q into mu P. What is the value of Na? Value of Na is 10 to the power 16 into 1.6 into 10 to the power minus 19. And what is the value of mu P? That is 380. So you will put it and you will get the value of this thing. Conductivity, Siemens per centimeter. Everything is going in centimeter only. So this answer you will get conductivity at T equals to 0. Now you need to find the conductivity as a function of time t. I will find out as a function of time t, then I will put t equals to infinity. For that what I need to use the formula of generation rate. This is given, which is 8 into 10 to the power 20 centimeter cube second inverse. From here I know that my this term is gone, and although this here I will apply it in minority carriers. So minority carriers are electron here. So this term is gone. But what about dN by dt? What I mean to say is that if I apply, is there anywhere steady state mentioned? What I am saying, steady state is mentioned or not? Steady state is not mentioned. So what you will say, sir, I will have to apply this particular thing. That would be equals to generation rate minus recombination rate. Now in your answer, what you require? Delta NT you require, delta PT you require. What you require? Delta NT. What delta NT would be equals to? You know that rise will be exponential. So delta NT would be equals to whatever the excess carriers that you are going to generate at steady state. What is delta N? Delta N is excess electrons at steady state. You know that this is where I will be reaching. This is where I will be reaching using the exponential form. So actually what you require? You require excess electron concentration at steady state. Are you able to understand what I am saying? Sir, I thought of applying continuity equation. Then I saw that I have the generation rate, but I don't have the recombination rate. I am stuck here. Then I thought, what I require, sir? I require conductivity, sir. Now in the conductivity, sir, number of electrons and number of holes I will be requiring. In number of electrons and in number of holes, there will be excess carrier generated. So that is my matter of concern, sir. I need to find excess carrier generated as a function of time t. I know that they will be rising as a function of time t. But if I know the steady state value, that means these many electron hole pair will be generated, sir. If I know that particular value, then sir, my job will be done. So yes or no? Are you able to understand what I am saying? And that means you will apply this equation, but you are applying the equation at steady state only. I am applying the continuity equation, although dN by dt is not always equals to 0, but at the steady state it will be equals to 0, no? So what I will say is that at steady state generation rate is equals to recombination rate. So generation rate is equals to recombination rate, that would be equals to the excess carrier concentration, which is delta N divided by tau N. It would be a function of x, but it is not a function of x. Why is that so? Because it is constant, uniformly distributed. So it is not a function of x, it is constant. So from here I can find the value of delta N. What will be the value of delta N? That would be simply generation rate into tau N. So 8 into 10 to the power 20 into 5 into 10 to the power minus 7. So 8 into 10 to the power 20 into 5 into 10 to the power minus 7. 40 into 10 to the power 13 centimeter cube inverse. So this is the value of delta N you are having. So now you can find out the value of delta NT as well. So your delta NT would be equals to 4 into 10 to the power 14 1 minus e to the power minus t by tau. What is the value of tau? Tau is 0.5 micro, right? 0.5 micro, 0.5 micro. So this is the value of delta nt, which would be equals to value of delta pt as well, right? So if I add a page, now I have find out the value of delta nt and delta pt. So your sigma t is equals to, sir, one value will be this value I already know, 0.608, 0.608 plus delta nt q mu n plus delta pt q mu p. Now I know that 0.608 plus, sir, I know delta nt will be equals to delta pt. So the value will be 4 into 10 power 14, and everything is going in centimeter cube, right? Everything is going in centimeters. So 4 into 10 to the power 14, 4 into 10 to the power 14, 4 into 10 to the power 14 into 1 minus e to the power minus t by 0.5 micro. Sir, this I have taken common. Q also I can take common. Q also I can take common, which will be 1.6 into 10 power minus 19. And sir, in the bracket mu n plus mu p will come. So what is the value of mu n plus mu p? Mu n plus mu p. That is 1280. Are you able to understand what I am doing here? Say yes or no. So what you will see, 0.608 plus 4 into 10 to the power 14, 1280. So that would be 1.28, 10 to the power 3, 10 to the power 17, 10 to the power minus 2. So what I will do is that 4 into 1.6, 4 into 1.6 into 1.28, 4 into 1.6 into 1.28, 4 into 1.6 into 1.28, 10 to the power 3, 10 to the power 17, 10 to the power minus 2. 0.081. Yeah, okay. So what we are getting, 0.081. This much we are getting, right? Okay. So if you solve these things, this is what you are getting, 0.081 into 1 minus e to the power minus t by 0.5 micro. This is your delta nt. Now they could have asked at any value. When you solved it, what error did you do? You forgot to take, sir, this thing into action. Sorry, this was the minority, so you forgot to take this thing into action. You know that, sir, because of the thermal equilibrium something would come. Then you forgot about the excess majority charge carriers as well. Excess majority charge carriers. That means you forgot about the excess holes as well. These many holes were already there, but excess holes will also come into action. So those you forgot about, and then you messed up the question, right? And secondly, what is the second thing? Here also you thought that, sir, I cannot apply generation rate equals to recombination rate, which is correct. But what I require the concentration at steady state only. That's why I can apply the generation rate equals to recombination rate formula. Everything is correct. Everything is absolutely fine, right? So if I need to find at infinity, what I will do, I will put t equals to infinity. That means it is simply the steady state. At steady state means electron hole pair are being generated. So because of the excess carriers, this much things is coming into action. Because of the excess carriers, this much conductivity is increasing. So 0.608 plus 0.081. So 0.689, which was pretty simple. I should not have solved it. 0.689 Siemens per centimeter. So this is the answer that we are getting. All good, all fine. So this question is also solved. Only the good question I am picking up. You would go to the gate PYQs, you will see that, sir, they are nothing. We are able to solve the gate PYQs, sir, in one go. These are not there in the gate PYQs, okay? These are pretty good questions. I am picking only the selected ones. Those are pretty good. Now this is a gate PYQ. You will be very easily able to solve. The band gap for gallium arsenide is 1.42 electron volt. And intrinsic carrier concentration is also given. In order to generate electron hole pair, what kind of wavelength should be there? You know that the applied energy should be greater than the band gap energy. That means Hc by lambda should be greater than the band gap energy, which is equal to 1.42 electron volt. What is the value of Hc? 1242 electron volt nanometer divided by lambda. That should be greater than 1.42 electron volt. So electron volt to electron volt is getting cancelled out. So lambda should be less than 1242 nanometer. This is coming here 1.42. So from here, what do you see? Lambda should be lesser than 1242 divided by 1.42. Answer is coming in nanometer. So this is the answer we are getting, 874.64 nanometer. But I need to convert it into the micrometer. So answer will be 0.87 micrometer. So lambda should be less than 0.87 micrometer. So as per you, this should be the answer, 0.87 micrometer. Now sir, this lower limit is also given. Sir, this lower limit is also given, no? Lower limit of lambda means higher limit of energy. What I am saying, lower limit, what is the energy? This is the energy that we are giving. Lower limit of lambda means higher limit of energy. That means they have given the higher limit of the energy. What is the lower limit of the energy? That at least you need to give 1.42 electron volt, then only electron hole pair will be generated. But you cannot give very high energy. What will happen? The electrons will gain very high energy. Since they are having very high energy, they will move very fastly and they will collide with the atoms, and because they will be colliding with the atoms, the heat will be generated, and that heat will be burning out your device. Okay. Or what may happen is that you have given so much of high energy that you are able to cross the work function. What is work function? You might have studied in your class 12th. If you haven't studied, don't worry about that. Work function will come into action in EDC as well. So you have given so much of high energy that electron will try to escape from the material. So this can also happen, but that is very impractical. What will happen is this, that I have written. If the wavelength is very small, that means photons are having very high energy, then electron will get excited with extra energy higher than the band gap. This extra energy will not help in creating more carriers. What it will do? Electrons will quickly lose it as a heat to the lattice. This process is called thermalization, where carriers will give up the excess energy to the vibrations of the crystal. Okay, and hence photons below a certain wavelength should be photons below a certain wavelength are not practically useful, which defines the lower limit of the range. So this limit is practically defined, you cannot calculate it. Are you able to understand this point? That means wavelength should be lesser than this and wavelength should be greater than some other thing as well. That wavelength should be greater than some other thing as well. What is, how much it should be greater, that is practically defined. But you can see that they have framed the option smartly, that all the options are different here. Okay, so lower limit you cannot define, but higher limit you can define. Similarly, for the energy you can define the lower limit, but you cannot define the higher limit. That means you cannot give very high energy to any electron, and if you give very high energy, then your device may be burning out. Well and good. Let's solve this question. This is also a good question. A germanium sample of dimension 1 cross 1 centimeter square is illuminated with 20 milliwatt and 600 nanometer laser light as shown in the figure. What do you understand? 20 milliwatt is the power. That means you are giving 20 millijoule energy per second, and 60 nanometer is the wavelength of a photon. That means you can find out the energy of one photon, right? The illuminated sample surface has a 100 nanometer lossless silicon dioxide layer that reflects 1/4 of the incident light. What do you mean by that? That means if I intensity of light is coming, then 1/4 will be reflected back. That means I by 4 will be reflected back, and 3I by 4 will be getting in. 3I by 4 will be getting in. So this is your silicon dioxide, SiO2, and this is my germanium. So let me make it a bit more bigger. This is the scenario here. So I intensity of light was coming, I by 4 was reflected. This much we have studied. Okay, from the remaining light, 1/3 of the power is reflected from the silicon dioxide and germanium interface. So this is your SiO2 and this is your germanium, and this is your SiO2 germanium interface. This is your SiO2 germanium interface. So I by 4 was reflected, so 3I by 4 came into here. Now out of this 3I by 4, 1/3 of this is from the remaining light, 1/3 of this power. Okay, they are talking about power, so they are not talking in intensity. Intensity and power both are the same thing actually. Okay, intensity and power both are the same thing. From the remaining light, 1/3 of the power reflected from the silicon dioxide interface. That means from here, 1/3 of this. What will be the 1/3 of this thing? That would be half. Sorry, P by 4. 1/3 of this will be P by 4. So from 3P by 4, P by 4 is reflected from here. Then how much is going here? P by 2. So inside the germanium, how much is going? P by 2. 1/3 and okay, 1/3 of the power is reflected from the silicon oxide germanium interface. 1/3 is absorbed in the silicon layer and 1/3 is transmitted through the other side. So now here P by 2 is coming. Okay, here P by 2 is coming. Now this total power was 3P by 4. 1/3 of this, what will be the 1/3 part? P by 4, P by 4 and P by 4. So these are the 1/3 parts. So 1/3 part is reflected back, this P by 4 is gone, and 1/3 part here will be eaten up. 1/3 part of 3P by 4, that would be P by 4. So this will be eaten up by the germanium, or you can say that what they have said, 1/3 is absorbed in the germanium and 1/3 is transmitted, and here P by 4 is transmitted. Is the diagram clear to you or not? P came, P by 4 gone, then 3P by 4 was there. Now 3P by 4 is having 3 parts, P by 4, P by 4, P by 4. So P by 4 was gone from here, P by 4 was eaten up, and the remaining P by 4 is getting out. Okay, absorption coefficient, what they are saying, 1/3 is transmitted through the other side. If the absorption coefficient of germanium at 600 nanometer is 3 into 10 power 4 centimeter inverse and band gap is 0.66, then the thickness of germanium layer up to 3 decimal places. Okay, so here how much light came into action? P by 2. In the germanium layer, what we are talking about, we need to find out the thickness of germanium layer. So P by 2 light came into action. When it covered the distance of T, the intensity became P by 4. Started with P by 2, by covering the distance of T, P by 4 was the final output. That means what I am saying is that if in the germanium, if there is power P, not P, I will say P dash, and if I cover the distance of T, then eventually I will be getting out with P dash by 2. This is the scenario. Or you can see here is that you started with P by 2, when you got out, you had P by 4. So I started with P by 2, it will exponentially decrease. Now some coefficient is given. What is that coefficient? Absorption coefficient is given. So that absorption coefficient is having a unit of centimeter inverse. What it is having? It is having a unit of centimeter inverse. So what I will write down here? E to the power minus alpha x. So this is your, I would say, power with respect to distance x. Power with respect to distance x. So if I have covered a distance of t, my power has become P by 4. So this was actually P by 2 and this was actually P by 4. So if I cover the distance of t, my power has become P by 4. So initially it was P by 2, I covered the distance of t, it has become P by 4. So what you will see here is that P and P will get cancelled out, it will become ln2 divided by alpha. That would be equals to t, because alpha is having a unit of centimeter inverse. When it goes upward, it will become centimeter. So this is the answer, ln2 divided by, what is the value of alpha? 3 into 10 to the power 4. 3 into 10 to the power 4. Centimeter inverse, right? Centimeter inverse. So if I solve it, what do I get? 0.231, 0.231, but in micrometer you need to tell. So 23.10. Yeah, this is the answer. ln2 divided by 3 into 10 to the power 4 was there. So answer was coming. This was the answer in centimeter. So ln2 divided by 3 I did. So what answer I was getting? 0.231. So 0.231 into 10 to the power minus 4. I need to make 10 to the power minus 3. So if I am multiplying with 10 to the power minus 2, so here I need to multiply with 10 to the power 2 as well. So what you are getting? 23.1 micrometer. Okay, 23.10 micrometer. So this is the answer. Well and good. Although in the examination what they are saying, rounded off to 3 decimal places. What does that mean? I should write down 23.104. In the examination, the answer should have been written as, this is how you should write down the answer, 23.104 micrometer. This answer should be written. There you go, that's it. Okay. Now this is the question that is left. So that we will solve in a separate video. Okay, I will make a separate video for this particular question. So this lecture is completed. I hope you enjoyed it. It might seem tough at a, like, I don't think when you have completed the lecture it will feel like tough topic. It will be very easy topic for you. Although it is not completed, the beauty lies in this particular question as well. So I will make a separate video for this particular question because I will be uploading on YouTube as well. So this solution will go on YouTube as well because need to give the solution, right? We need to give the solution to some people. Those people should know that what is known as quality actually. Okay, so we will do that. I hope the concept is clear. You can try this question on your own. You can try this one on your own. Let's see if you are able to solve. Will be very tough to solve. Will be very, very tough to solve. Like GATE AIR1 in 2022 examination, he was not able to solve it. So you try solving it, and let's meet in the next lecture. Okay. So in the next lecture, I will solve this particular question only. Okay then. And after that, we will start our Fermi direct distribution. Yeah. Thank you very much.